Right now, planet Earth is bursting with life, rainforests thick with millions of species, coral reefs stretching for miles, humming with colour, oceans teeming with whales, fish, plankton, an entire web of existence so complex we still haven't mapped all of it. Life feels permanent here, unstoppable even. However, if you had looked at this planet 252 million years ago, right at the end of what geologists call the Permian period, you would have witnessed something almost impossible to comprehend. Somewhere between 90 and 96% of all marine species gone. Around 70% of land animals wiped out. Entire ecosystems that had taken hundreds of millions of years to build, collapsing in what might have been less than 100,000 years, maybe even faster than that. Not a slow fade, not one bad season, a near total reset of life on Earth, so severe that scientists just call it the Great Dying. Think about that phrase for a second. Not an extinction, not a crisis. The Great Dying. Out of the 5 major mass extinctions in Earth's history, this one stands alone as the worst. Worse than whatever killed the dinosaurs. Worse than anything before or since. And here's the part that should genuinely unsettle you. Scientists still aren't entirely sure exactly what triggered it, or why it became so catastrophic. If you're listening to this while falling asleep, that's exactly why I make these. So subscribe maybe, and tell me where you're listening from and what time it is right now. I actually check the comments, and it's wild seeing it all lined up. Tokyo at sunrise, London at midnight, Chicago somewhere in between, everyone drifting off together without even knowing it. And if you want to really support what I'm doing here, Spotify is honestly the best way. Follow me there, and if you've got a second, drop a 5-star review. There's a link down in the description. It genuinely helps more than you'd think. Okay, back to the mystery, because that's really what this is. A 252 million year old mystery written into rock, buried in ancient seafloors, locked inside fossilized bones and blackened carbon layers. Something happened at the end of the Permian that pushed our planet's life support systems past their breaking point. The question is, what was it a single catastrophic trigger? Or a chain reaction, one disaster setting off another, spiraling out of control? Scientists have spent decades chasing clues buried in Siberian rock formations, in ocean sediments, now sitting exposed on mountaintops, in the chemical fingerprints locked inside ancient shells and teeth, and slowly a picture has started to emerge. A picture of a planet that didn't just get unlucky. A planet where multiple systems, atmosphere, oceans, land, all seem to have failed together, feeding into each other, amplifying each other, turning a bad situation into something almost unimaginable. Over the next while, we're going to dig into this from every angle. We'll look at what Earth actually looked like before the collapse, what the rocks and fossils are telling us, how scientists reconstructed disaster that happened 250 million years ago. We'll trace the timeline, hunt down the prime suspects, follow the carbon, the sulfur, the acid, all the way down into the oceans and up into the skies. And by the end we'll ask the question that matters most. What does the worst extinction in Earth's history tell us about the planet we're living on right now? Let's go back, way back, 252 million years, to a world that was about to change forever. Picture Earth 252 million years ago, and the first thing you'd notice is that it doesn't look like home. There's no scattered patchwork of continents separated by blue ocean. Instead, almost every landmass on the planet has crushed together into one massive supercontinent. Geologists call it Pangaea, and it's an absolute unit. Stretching from pole to pole, one single connected mass of rock and dirt surrounded by a single world-spanning ocean called Panthalassa. Now, you might think one giant continent sounds simple. It's not. It's actually a recipe for extremes. When you jam that much land together, you kill the moderating effect that oceans normally have on climate. Water heats up slowly and cools down slowly. Land does the opposite. It swings wildly. So the interior of Pangaea, thousands of miles from any coastline, became a furnace. Daytime temperatures soaring, nighttime temperatures crashing, seasons flipping between brutal heat and biting cold with almost nothing in between to soften the blow. Vast deserts spread across the continental interior, redder and drier than almost anything we have today. Sand dune fields stretching farther than the eye could see. And where you did get rainfall, it wasn't gentle. It came in violent monsoon pulses, flooding river systems for a few wild weeks before drying up again for months. This wasn't a planet of gentle equilibrium. It was a planet already living on the edge of its own extremes, long before anything went catastrophically wrong. The oceans, meanwhile, were running on a very different rhythm than the ones we have now. Modern oceans are kept alive by circulation, cold water sinking near the poles, sliding along the ocean floor, dragging oxygen down into the depths before rising again thousands of miles away. It's basically the planet's respiratory system. Permian oceans had their own version of this circulation, but it was more fragile, more dependent on temperature gradients that, as we're about to see, were sitting right on the verge of collapse. And on top of all that, life had built something remarkable. For tens of millions of years, evolution had been quietly constructing some of the richest, strangest ecosystems the planet had ever seen. In the seas, coral-like reefs bloomed across shallow tropical waters, not built by the corals you'd recognize today, but by sponges and calcifying algae, all wrapped around a staggering variety of shelled creatures. Brachiopods carpeted the seafloor by the millions. Trilobites, ancient armoured survivors that had already been around for nearly 300 million years, were still creeping through the muck. Ammonites drifted through open water, their coiled shells ranging from coin-sized to dinner plate enormous. Crinoids, these strange plant-looking animals related to starfish, formed underwater meadows that swayed in the current like fields of stone flowers. On land, things were just as strange. Forget dinosaurs, they hadn't shown up yet. This was the age of the synapsids, the distant ancestors of mammals. Creatures like Dicynodon, stocky, tusked, somewhere between a pig and a turtle in general vibe, grazing in herds across the floodplains. Gorgonopsids stalked them, saber-toothed predators that looked like nightmare fusions of a wolf and a reptile. Vast conifer forests and seed fern woodlands stretched across the wetter regions. Insects buzzed in numbers and varieties we're still cataloguing from the fossil record. This was a fully mature, fully established biosphere. Hundreds of millions of years of evolutionary refinement, producing ecosystems that on the surface looked stable, permanent even. But here's the uncomfortable truth hiding underneath all that apparent stability. Success in one set of conditions can become a liability the moment those conditions change. Many Permian marine species had evolved within a fairly narrow temperature and chemistry range, an ocean that had been relatively steady for millions of years. Their bodies, their shells, their metabolisms were finely tuned instruments, built for a world that stayed within certain boundaries. Push those boundaries even a little, and things that seemed perfectly adapted suddenly become perfectly vulnerable. That's actually the core idea behind what scientists mean when they use the phrase mass extinction. It's not just a bad year for wildlife. In the deep time record, a mass extinction is defined as a geologically rapid loss of a significant percentage of Earth's species, across multiple unrelated groups, in both the oceans and on land, all within a narrow window of geologic time. We're talking thresholds like losing more than 75% of species, and doing it fast enough that it shows up as a sharp line in the rock, not a gradual fade. By that definition, The end of the Permian isn't just the biggest of the 5 recognized mass extinctions. It's in a category almost by itself. And to understand how a planet this alive, this established, this seemingly permanent could come apart so completely, we need to start reading the only witnesses that were actually there. The rocks, the fossils, the chemical fingerprints left behind in stone that's been waiting 252 million years to tell its story. When geologists say the rocks remember, this is what they mean. If you could slice into a cliff like a layer cake and walk sideways through time, you'd eventually hit the moment when the Permian world ends and the Triassic begins. That contact is our crime scene tape. It's called a boundary, and the science of reading those layers is stratigraphy. In its simplest form, stratigraphy says younger stuff gets laid down on top of older stuff. Sediment settles, hardens into rock, and over millions of years you get a vertical stack of former worlds. Each layer is a snapshot of conditions when it was formed, what the rivers were doing, what the ocean chemistry was, which creatures were alive, which ones weren't. So if something truly global and truly catastrophic happens, it doesn't just kill things, it leaves a mark in the stack. At the end of the Permian, that mark is surprisingly sharp. You can walk up to outcrops in China, in Italy, in Greenland, in South Africa, and see a narrow band of rock, sometimes only a few centimetres thick, where everything changes. Below it, fossil-rich Permian limestone with thriving reef faunas, burrow traces, shells packed like gravel on a beach. Above it, a different world. Fewer fossils, different species, different sediment textures and colours. That thin interval is what stratigraphers call an event horizon, the layer that records the main pulse of the catastrophe. Sometimes it's not just a change, it's a gap. In some sections, the boundary is marked by an erosional surface, a scoured, irregular contact where older rock has been shaved off before new sediment was laid down. To a stratigrapher, a missing slice of time can be as important as a preserved one. It hints at sea levels dropping, coastlines reshaping, rivers cutting down through their old floodplains. In other places, the boundary is continuous but condensed, a very thin layer that represents a surprisingly long stretch of time, squeezed into just a few millimetres of mud or carbonate. These boundary layers and missing intervals are the first clue that something big and fast was happening to Earth's surface systems. But layers alone don't tell you which worlds they hold. That's where fossils come in. When paleontologists talk about biodiversity through time, they're juggling two related but distinct ideas, diversity and abundance. Diversity is how many different kinds of organisms exist in a particular place or interval, how many species, how many genera, how many ecological roles. Abundance is how many actual individuals there are. You can have a world with high diversity but low abundance, lots of different species, each rare and scattered, or a world with low diversity but high abundance, a few hardy generalists dominating everything. In many end Permian sections, both numbers crash, but not always in lockstep. If you look just below the boundary in places like the Maishan section in China, you see a rich, varied marine fauna, multiple brachiopod species, ammonoids, crinoids, sponges, algae. Then, across that boundary, the roster collapses. Whole groups vanish. That's a diversity hit. At the same time, the fossils that do remain often get sparser and more patchy in the rock. Sediment slices that once contained thousands of shells now hold a few scattered survivors. That's an abundance crash layered on top of a diversity crash. Tracking both is crucial, because you can lose abundance temporarily, say during a short drought or cold snap, without permanently losing species. The Great Dying is different. The fossil record shows not just ecosystems thinned out for a while, but entire lineages disappearing from the stack and never coming back. Still, fossils and layers only give us sequence: before, during, after. To understand how fast this happened, we need a clock. For deep time, that clock is radiometric dating. Some minerals, especially in volcanic ash layers, contain radioactive isotopes that decay into stable daughter products at known rates. Uranium turning into lead, for instance, works like a slow, predictable hourglass. If you can find a thin volcanic ash bed just below the extinction horizon and another just above it, you can date each one and bracket the event between two numbers. That's exactly what's been done at several key boundary sections. High-precision uranium-laid dating of zircons in ash beds pins the main extinction pulse at around 252 million years ago and suggests that the sharpest phase of the die-off, at least in some marine settings, may have unfolded over something like tens of thousands to a few 100,000 years. That's geologically instant. Not an afternoon, not a single storm, but a few ticks of the clock interval in Earth's deep history where most complex life nearly vanished. Once you have those dates and those characteristic fossil changes, you can start playing the global correlation game. You match up the boundary in a South Chinese carbonate platform with a Siberian deep water basin, with an Italian cliff, with a Karoo Basin river plain in South Africa. You look for the same extinction pattern in the fossils, the same geochemical shifts, the same ash layers or magnetic signatures. If multiple places, separated by whole oceans, show the same sequence of changes pinned to the same radiometric ages, you're not looking at a local disaster. You're looking at a planet-wide event. In the end Permian case, that's exactly what the stratigraphic puzzle pieces show. Marine sections from Europe to China to South America all record a similar turnover near 252 million years ago. Continental sections on Pangaea's interior show their own version. Plant communities collapsing, river systems reorganizing, unfamiliar assemblages of survivors taking over. Different environments, same timing. The rocks are all pointing at the same gun. But as clean as this sounds, the picture is not perfectly sharp. There are uncertainties built into every step. Radiometric dates have error bars. Even our best techniques give ranges, not single magic numbers. And when you're trying to resolve events that may have taken tens of thousands of years, a plus or minus of a couple 100,000 can blur the sequence. Sedimentary layers themselves don't accumulate at a steady pace. A centimetre of mud in one basin might represent a decade. In another, it might represent 10,000 years with long, quiet pauses. Then there's sampling. The fossil record is wildly uneven. Some environments preserve shells and bones beautifully. Others erase almost everything. Some regions of the world are riddled with accessible outcrops and have been studied intensively for a century. Others are remote, buried, or politically inaccessible. When paleontologists say 90% of species went extinct in this group, that's a careful estimate built out of incomplete collections, statistical corrections, and assumptions about how well different rock types and regions preserve life. There's also the problem of resolution. Even with dense sampling, it's hard to see very short-lived events, things on the scale of years to centuries, in rocks that average everything together over thousands of years per layer. A brief, brutal heat spike or a sudden pulse of ocean poisoning might show up only as a smeared signal, a slightly thicker boundary, a subtle chemical anomaly. We know the Great Dying was fast in geological terms, but exactly how fast in human terms, how many generations of Permian animals actually lived through the unravelling, that's still an open question. So when we say the end Permian extinction happened around 252 million years ago and wiped out the majority of species on Earth, we're not reciting a simple textbook fact. We're summarizing a huge, constantly updated jigsaw puzzle built from boundary layers, missing intervals, fossil counts, ashbed clocks, and cross-continental correlations, all filtered through the hard realities of what rock will and won't preserve. And once you accept that basic skeleton of the story, The timing, the scale, the global reach. Another, even more unsettling question comes into focus. If the stratigraphy tells us when the biosphere died, can it also tell us how? To answer that, we have to zoom into the collapse itself and ask whether Earth's worst extinction was a single hammer blow or a long, stuttering fall down the stairs. If you zoom in on that fall down the stairs, the first thing you notice is that different parts of the house remember it differently. In the oceans, especially along the shallow continental shelves of what's now South China and Italy, the extinction looks brutally sharp. One moment you are in a busy Permian reef full of brachiopods, fusilline forams, sponges, corals, algae, all stacked on top of each other like a crowded apartment block. A few centimetres higher in the rock, the building is empty. The fossil record there really does look like a single, catastrophic crash at the famous Methane section in China, where a lot of the timing work has been done. The main marine extinction pulse is crammed into what might represent less than 100,000 years. Some estimates, depending on how you read the sedimentation rate, shrink it to something more like tens of thousands. In deep time terms, that's a heart attack, not a slow decline. You see the same pattern in other marine sections, a last burst of diversity just below the boundary, then an abrupt pruning where whole groups vanish at once. Ammonoids that had been diversifying drop to a handful of surviving lineages. Reef builders go from complex frameworks to microbial mats. Trace fossils that record burrowing activity thin out or disappear. For many marine communities, the Great Dying doesn't look like a long illness. It looks like a cliff, but not everywhere. If you step away from the shallow tropical shelves and look at some deeper water marine basins, or you move onto the continents and study river plains and coal swamps, the story stretches out. In the Karoo Basin of South Africa, for example, where we have one of the best records of land vertebrates across the boundary, the extinction of Permian animals like the Dicenodonts and Gorgonopsians doesn't all pile up at a single horizon. Some lineages taper off earlier, some hang on longer. Plant communities in places like China and Australia show multiple episodes of stress and turnover before the final crash. This is where the debate really kicks in. Are we looking at one short, focused destruction event that different environments record with different levels of blur? Or did the end Permian extinction unfold as a series of distinct blows spread over hundreds of thousands of years, with the main boundary just marking the worst hit? Many researchers now favour a pulsed scenario, especially on land. In this view, the long-term background conditions were deteriorating for a while. Climate warming, changing rainfall patterns, maybe early hints of ocean anoxia, and acidification, causing earlier, smaller extinction pulses. Then, near 252 million years ago, the system crosses one or more thresholds, and you get the big synchronous marine crash, plus an amplification of the terrestrial crisis. There's some direct evidence for this. In several marine sections, geochemists see more than one negative carbon isotope excursion, a signal that the carbon cycle was being disturbed in multiple bursts, likely by repeated injections of CO2 or other greenhouse gases into the atmosphere-ocean system. Fossil assemblages sometimes show corresponding stepwise losses, a first wave of sensitive species vanishing, then a partial stabilization, then a second, more devastating wave where even hardy generalists disappear. On land, plant fossil records in some regions show what look like prelude events. Forests thinning, spore-producing opportunists briefly taking over, then partial recovery, then another crash closer to the marine boundary. Vertebrate faunas show staggered disappearances of different groups rather than a single moment when everyone drops out. So how do you reconcile a seemingly instantaneous marine kill zone with a more drawn-out terrestrial decline and hints of multiple pulses in both realms? Part of the answer is that rocks don't all keep time the same way. A reef in a shallow tropical sea can pile up limestone quickly and continuously, capturing very fine-scale changes. A river floodplain might only get a big pulse of sediment during occasional floods, leaving long gaps in between. Deep basins can quietly accumulate mud at a steady trickle, or they can starve for sediment for long intervals. The resolution you get depends on where you're looking. Imagine trying to reconstruct a city's blackout from different security cameras. One camera takes a photo every second, another only clicks once every 5 minutes. A third goes dark whenever it rains. The same blackout will look sudden, stepped, or even invisible depending on which camera you trust. The Permian Triassic boundary works the same way. Marine carbonate platforms are high frame rate cameras. Some continental basins are more like occasional snapshots. There's also the question of ecological thresholds. Ecosystems aren't infinitely elastic. You can push them a little higher temperatures, slightly more acidic oceans, a bit less oxygen, and they flex, adjust, shuffle species around. Push them too far or too fast, and you hit a tipping point where the whole structure reorganizes. An ecological threshold is that invisible line. Before you cross it, the reef is stressed but functioning. Some species decline, others become more common, but the basic architecture holds. Cross it, and the framework builders die in large numbers, the physical structure breaks down, sediments change, and a completely different kind of community takes over. The shift can be rapid, even if the pressures that pushed it took a while to build. That helps explain how the end Permian extinction can look both prolonged and sudden. The underlying drivers, whatever they were, may have been ramping up over hundreds of thousands of years, causing preliminary pulses of extinction and stress. But once key thresholds were crossed in the climate system, in ocean chemistry, and in terrestrial hydrology, multiple ecosystems around the world may have flipped almost simultaneously into new degraded states. From the perspective of the biosphere, that synchronicity is the real catastrophe. This is why geologists and paleontologists get so fixated on global timing. If shallow marine faunas in China, deep basins in Armenia, and river ecosystems in South Africa all show their major break at essentially the same radiometric ages, you've probably hit one of those planetary tipping moments. It's not just that a lot of species died, it's that multiple independent systems failed together. What could do that? What kind of forcing is big enough and sustained enough to warm the planet, destabilize the carbon cycle, strip oxygen from the oceans, upset rainfall patterns on land, and push such different environments over their thresholds within roughly the same window of time? To answer that, we have to look upstream in the rock record, away from the boundary layer and into the deep, dark plumbing of the planet itself. To the place where, around 252 million years ago, the crust opened up and began to pour out one of the largest volcanic outbursts in Earth's history. When geologists went hunting for that kind of planetary scale forcing, their trail led them to a place that at first glance doesn't look like much of anything. Northern Siberia today is mostly flat, boggy and cold. But buried under the permafrost and worn down hills is the frozen corpse of a volcanic event so vast it's hard to wrap your head around it. It's called the Siberian Traps, and it's not a single volcano. It's a whole geological province, the surface expression of the planet's deep plumbing gone berserk. In technical terms, the Siberian Traps are a large igneous province. That phrase sounds dry, but what it really describes is a volcanic flood on a continental scale. Instead of cone-shaped volcanoes spitting out lava now and then, you get huge fissures opening in the crust, kilometers long, pouring out sheets of basalt that can cover areas the size of countries in a matter of years or decades. Do that not once, but over and over, and you don't just get a lava field. You resurface a chunk of a continent. The volumes involved are staggering. Estimates vary, but the total amount of lava erupted in the Siberian Traps is on the order of several million cubic kilometres. Imagine burying the entire continental United States under a layer of basalt, a kilometre thick, and you're in the right ballpark. And that's just the lava we can still see at the surface. There's also a huge system of intrusive rocks, sills and dikes that force their way into older sediments underground, cooking them from within. Just as important as the size is the tempo. This wasn't one gigantic explosion that came and went in a weekend. Geochronology suggests that the main phase of Siberian Traps magmatism lasted on the order of a few 100,000 years, maybe up to 1 million if you include the tails. Within that envelope, there were pulses, episodes of especially intense eruptive activity, separated by quieter intervals. That pulsed behaviour matters, because it lines up suspiciously well with those multiple carbon cycle disturbances and extinction steps we saw in the last section. Each major surge of magma to the surface or into the crust would have been a fresh insult to the climate system. A new dose of gas, a new shove toward instability. What made those eruptions so dangerous wasn't just the lava. It was the invisible stuff they released. Every big basalt province is a gas factory. When magma rises and decompresses, gases that were dissolved under high pressure come bubbling out. Carbon dioxide is the most famous culprit, and the Siberian Traps would have belched staggering amounts of CO2 into the atmosphere, both directly from the magma and indirectly by baking carbon-rich sediments. Think coal measures, organic-rich shales, even evaporites loaded with sulfur and halogens. As hot intrusions sliced through them, they would have released their own chemical ghosts, CO2, methane, sulfur compounds, chlorine, fluorine, into the air and oceans. Sulfur dioxide is a key part of that mix. Injected high into the stratosphere, SO2 reacts to form tiny sulfate aerosols that reflect sunlight. In the short term, years to decades, big volcanic sulfur releases can actually cool the planet. We've seen that in the historical record with eruptions like Pinatubo in 1991. Global temperatures dip for a few years because more sunlight is bounced back to space. So you've got this paradox. The same eruptions that are blamed for runaway greenhouse warming can also produce temporary volcanic winters. How do you get from one to the other? The crucial difference is persistence and balance. Sulfur aerosols fall out of the atmosphere relatively quickly, on the order of a couple of years. Carbon dioxide hangs around for centuries to hundreds of thousands of years in the climate system. If you have a single big eruption, the short-lived cooling can dominate. But if you have repeated outpourings over hundreds of thousands of years, each producing a brief cool snap but steadily ratcheting up CO2, the long-term trend is warming, and the Siberian Traps weren't just a sulfur and carbon machine. Those magmas and the rocks they torched also released halogens, chlorine and fluorine compounds that can damage the ozone layer, break down enough ozone and more ultraviolet radiation reaches the surface. That's bad news for land plants, plankton, and anything else that has to live in the top few meters of the ocean or breathe unfiltered air. Combine that with acid rain from sulfuric and hydrochloric acids, and you start to see a cocktail of stresses: poisoned soils, damaged leaves, eroded nutrients, weakened food webs, and organisms already living close to their thermal limits being hit from another direction. Layer that on top of the physical changes to the landscape. Lava flows smothering ecosystems, heat and wildfire flaring around eruptive centres. Rivers rerouted and blocked. This isn't one single killing mechanism, it's a cascade triggered by the same underlying engine. Still, there are caveats. Even though the Siberian Traps overlap in age with the end Permian extinction, nailing down the exact timeline to the precision we'd like is hard. Different labs get slightly different dates. Some studies suggest the main eruptive pulse might precede the sharpest part of the marine extinction by tens of thousands of years. Others find a tighter fit. It's clear they're broadly coincident, but whether individual lava pulses match specific extinction subpulses is still being worked out. There's also the question of geography. The vents were in what is now northern Siberia. Did their effects start as a regional catastrophe that later spread globally, or were the atmospheric and oceanic consequences effectively global from early on? Climate and ocean models generally say you can't dump that much gas into the system without worldwide consequences. But when you zoom in on the rock record, some regions show early, intense disruption, while others lag or record a more muted signal. That could be about real regional differences in how the crisis unfolded. It could also be about gaps and blind spots in our archives. So the Siberian Traps sit at the top of the suspect list. A colossal, pulsed, large igneous province spewing CO2, SO2, halogens and aerosols into the sky, capable in principle of driving both short-term chills and long-term fever, acid rain and ozone damage, ocean chemistry shifts and climate whiplash. The broad circumstantial evidence lines up, but to understand how that volcanic forcing actually translated into a planet that overheated, lost its breath, and nearly lost its biosphere, we have to follow the gases as they enter the climate system and change the rules of the game. To follow those gases, we have to start with something simple and almost boring sounding: radiative forcing. The basic physics were worked out long after the Permian, but the atmosphere back then played by the same rules it does today. Carbon dioxide is transparent to most of the visible sunlight coming in from space. That energy hits the surface, warms it up, and gets re-radiated upward as infrared. CO2, along with water vapor and a few other greenhouse gases, is very good at absorbing that outgoing infrared and re-emitting it in all directions, including back down. Add more CO2 and you thicken that insulating blanket. Less heat leaks to space, so the planet has to warm until radiation out once again balances radiation in. Climate scientists often describe this extra trapping in terms of watts per square meter, how much additional energy is being held in the Earth system. Doubling CO2 from pre-industrial levels today produces a radiative forcing of a few watts per square meter, and according to a lot of independent lines of evidence, something like 2.5 to 4.5 degrees Celsius of eventual global warming. For the end Permian, the numbers are fuzzier. We don't know exact starting concentrations, we don't know the precise shape of each CO2 pulse. But when researchers plug plausible gas release estimates from the Siberian Traps into climate models, they don't get a gentle nudge. They get a strong shove. Some simulations suggest atmospheric CO2 may have climbed to several thousand parts per million, 5, 10, maybe more times typical late Permian levels. Not instantly, and not in a single jump, but in repeated steps. Under those conditions, model worlds warm dramatically. Average global surface temperatures rise on the order of 5 to 10 degrees Celsius relative to the pre-crisis climate in many studies, with some scenarios producing even higher spikes in certain regions, especially on land. Now, 5-10 degrees might not sound like much if you're thinking in terms of daily weather. But remember, that's a global average, pooled across icy poles and tropical seas, night and day, seasons and storms. During the last ice age, when huge ice sheets covered North America and Eurasia, the planet was only about 4 to 6 degrees cooler than today. The difference between snowball Earth episodes and greenhouse hothouses through deep time often falls in that same small-sounding range. So pushing the climate upward by something like an ice age's worth of temperature change on top of an already warm late Permian baseline is not a tweak. It's moving the whole system into a different state. And it doesn't warm evenly. At the time of the Great Dying, most of the world's land was welded together into a single gigantic supercontinent, Pangaea. That geography changes how a CO2-driven fever plays out. Coasts are moderated by nearby oceans. Water has a huge heat capacity. It warms and cools slowly, and evaporation sucks up energy. Inland, far from the sea, you lose that buffer. On a big supercontinent, you can get continental interiors that are thousands of kilometers from the nearest ocean. Models and geological proxies for the late Permian and early Triassic converge on a similar picture. The heart of Pangaea becomes a heat engine. Summers there may have routinely reached temperatures that in modern terms would make the hottest days in today's hottest deserts look relatively mild. Think not just high 30s or low 40s Celsius, but sustained extremes above that. Nights and winters offer less relief, because the greenhouse blanket keeps more of the daytime heat from escaping. Poles don't escape either. Under high CO2, polar amplification kicks in. Ice and snow retreat, surfaces darken, and more sunlight gets absorbed rather than reflected. The temperature gradient between equator and pole shrinks. You end up with a weird combination: roasting continental interiors, toasty poles and sultry tropical seas. And then water vapour piles on. Warmer air can hold more moisture. That's just Clausius Clapeyron, a tongue twister of a law that says for every degree Celsius of warming, the atmosphere's capacity to hold water vapour rises by around 7%. Since water vapour itself is a powerful greenhouse gas, this becomes a feedback. CO2 starts the warming, warmer air, holds more water vapour traps, even more heat. The climate ratchets up. High humidity is also where biology starts to hit hard limits. Animals lose excess body heat mainly by radiating it away, and in many cases by evaporative cooling, sweating, panting, spreading saliva. That works only if the air is dry enough and cool enough for evaporation to proceed, and for heat to flow from body to air. Combine very high temperatures with very high humidity, and you approach what physiologists call a wet bulb limit. That's the temperature a thermometer would read if covered with a wet cloth and exposed to moving air. Humans and most large terrestrial vertebrates can't survive sustained wet bulb temperatures much above about 35 degrees Celsius. At that point, even a healthy, resting, naked body in the shade cannot shed heat fast enough to maintain safe internal temperatures. You cook from the inside out. We don't have Permian weather stations measuring wet bulb temperatures, but when researchers feed Permian geography and estimated greenhouse gas levels into climate models, some scenarios produce regions, especially in low-latitude continental interiors, where wet bulb conditions periodically approach or cross lethal thresholds for endothermic animals. Even if those extremes were seasonal or episodic, they would carve out zones where large land animals could not live year-round. Migration becomes mandatory. Any species without the mobility, behavior, or life cycle to dodge those peaks would be in trouble, even short of absolute physiological limits: high heat and humidity stress plants, insects and soil microbes. Reproductive windows shrink, growth slows, fire regimes change. A planet that feels like a sauna most of the time is a planet where a lot of organisms are living right on the edge of their comfort zone, with very little margin for additional insults. Warming also doesn't just sit there. It gets to work on the rocks. Higher temperatures speed up chemical reactions, including the weathering of silicate minerals in continental crust. When rainwater, slightly acidic from dissolved CO2, interacts with silicate rocks, it breaks them down, consuming CO2 in the process and carrying dissolved ions, calcium, magnesium, bicarbonate, down rivers and into the sea. Over millions of years, this silicate weathering thermostat helps stabilize Earth's climate. More CO2, more warmth, faster weathering, more CO2 drawn down. But that thermostat has limits, and it doesn't operate in a vacuum. You need not just warmth, but also liquid water and exposed rock. During the Permian Triassic crisis, higher global temperatures likely accelerated some aspects of weathering, especially in upland, wetter regions. Enhanced weathering and more intense rainfall in some belts would have boosted river discharge and nutrient delivery to the oceans, phosphorus, nitrogen, iron. That's fertilizer. In a normal world, it feeds productive coastal ecosystems. In a stressed, warming world, it can help tip marine basins toward eutrophication and oxygen loss. At the same time, some parts of Pangaea seem to have become hyper-arid. Sedimentary records from interior basins show evidence of dune fields and ephemeral rivers rather than stable, vegetated floodplains. In those regions, the land surface may have baked, cracked, and eroded in pulses instead of steady, gentle weathering. When rare storms did hit, they likely produced violent runoff events, flushing huge amounts of sediment and nutrients into downstream basins in short, destructive bursts. So you get this patchwork. Some areas with intense chemical weathering and heavy runoff, others drifting toward desertification, all feeding a global ocean that is getting warmer, more stratified, and more heavily loaded with nutrients. That sets the stage for what happens next offshore. Stagnant waters, expanding dead zones, and the slow suffocation of marine life. Running through all of this is the theme of feedbacks. CO2 from the Siberian Traps warms the planet. Warming boosts water vapor, which adds more greenhouse trapping. It alters cloud patterns in ways that are still tricky to model. Some clouds reflect sunlight and cool, others trap heat and warm, but overall, most scenarios for a super greenhouse world point toward reinforcement, not negation. Warming ramps up weathering and over long spans should help pull CO2 back down. But in the short term, that same enhanced weathering and runoff can fertilize the seas, fueling algal blooms. When that organic matter sinks and decays, it uses up oxygen and can release additional greenhouse gases, CO2, methane, even nitrous oxide, from oxygen-poor waters and sediments. Kill off forests on land with heat, drought, and acid rain, and you remove a major carbon sink. Exposed soils erode faster, releasing more previously stored carbon. Replace dark, transpiring canopies with bright, reflective rock or sand, and you change how the land surface absorbs and sheds heat and moisture. Some feedbacks push against change, others amplify it. What makes the end Permian so frightening is the growing evidence that, for a while, the amplifying loops were winning. Volcanic CO2 pushed the system, water vapor, ecological collapse, and ocean chemistry shifts helped keep it moving in the same direction. By the time those feedbacks really got going, Earth was no longer just a bit warmer. It was entering a different climatic regime, one where the oceans began to stagnate, where breathing underwater became difficult, and where the very basics of habitability were being rewritten. To see how that played out beneath the waves, we have to follow the heat into the deep, warm the surface of the ocean, and a few simple things follow. First, the physics. Cold water can pack in more dissolved gas than warm water. You can see this in your kitchen. A cold soda holds its fizz. A warm one goes flat faster. The same basic chemistry applies to oxygen in seawater. As surface temperatures climb, the maximum amount of O2 that can stay dissolved goes down. Even if the ocean were perfectly mixed, a hotter world would mean less oxygen available for anything with gills. But in a greenhouse world, the ocean doesn't stay perfectly mixed. Temperature also changes density. Cold, salty water is heavy and tends to sink. Warm, fresher water is lighter and tends to float. Under late Permian-style warming, the surface ocean in many regions becomes hotter and often a bit fresher, fed by rainfall and runoff, while deeper waters remain relatively cooler and saltier. that increases density contrast between layers and makes it harder for winds and currents to overturn the water column. This is stratification, the ocean settling into layers that don't easily mix. In a well-mixed ocean, surface waters absorb oxygen from the atmosphere and share it downward. In a strongly stratified ocean, the top layer hoards its oxygen, and what little trickles into the depths has to last a long time. At the same time, organic material, dead plankton, fecal pellets, bits of detritus, keeps raining down from the sunlit layer. Bacteria chew through that sinking food, and in the process they consume oxygen. If mixing is slow, the deep ocean becomes a one-way street. Oxygen in, oxygen used, none coming back. When oxygen levels drop close to zero, we call that anoxia. It's not a poetic term. It just means no oxygen. For most complex marine animals, fish, shellfish, cephalopods, big mobile invertebrates, persistent anoxia is a death sentence. They either flee if they can or they suffocate. Anoxia alone is bad enough. But it can get worse. In some environments, once oxygen is gone, a different kind of microbial community takes over. These microbes don't use O2, they breathe sulfate, a form of sulfur dissolved in seawater. In doing so, they produce hydrogen sulfide gas, H2S, the same stuff that makes rotten eggs stink. When that hydrogen sulfide accumulates in the water column, we call the condition ozonia, anoxic and sulfidic. Euxinic waters are not just oxygen-free, they are chemically hostile. Hydrogen sulfide is toxic to most animals and many plants, and in high enough concentrations it can even damage ozone if it reaches the atmosphere. A basin that tips into sustained ozonia is more than dead. It's poisonous. We can't sample late Permian seawater directly, but we can see its chemical ghosts in the rocks. Certain elements behave differently depending on how much oxygen is around. Molybdenum, for example, tends to be soluble in well-oxygenated seawater, but gets scavenged and locked into sediments under anoxic, especially sulfidic, conditions. Ion cycles between different forms, oxidized, reduced, that leave distinct mineral signatures. Sulfur isotopes, the relative abundance of different sulfur flavors, shift when sulfate-reducing bacteria are busily generating hydrogen sulfide. When geochemists measure these signals in organic rich shales and other marine sediments that straddle the Permian Triassic boundary, they see patterns that don't match a well-ventilated, healthy ocean. Many sections show strong indications of widespread oxygen depletion in bottom waters, and in some regions, especially in restricted basins, clear fingerprints of ozonia invading up into the water column. Not every core or outcrop tells the exact same story. Some show early intense pulses of anoxia, others suggest a more gradual expansion. That variability is part of the debate. Was the late Permian Ocean almost globally suffocating? Or was it a patchwork of deadly basins and marginal refuges, with oxygen-starved zones waxing and waning over hundreds of thousands of years? Most researchers converge on one broad conclusion. Ocean oxygen levels fell sharply during the crisis, and oxygen-poor conditions spread over far larger areas and to shallower depths than in normal greenhouse intervals. The precise geography and timing of maximum anoxia and ozonia, how high they climbed into the water column, how long they lasted in any given basin, are still active research questions. Lower oxygen does not just sit at the bottom quietly killing anything that wanders too deep. It rewires the entire food web. Start with plankton, the tiny drifters that harvest sunlight and form the base of most marine ecosystems. Warm, stratified surface waters can actually boost their growth at first, especially if nutrient-rich runoff from land is pouring in. You get big blooms, clouds of algae and other microorganisms feasting on the fertilizer. But those blooms come with a catch. When they die and sink, the decay process burns through more and more of the limited oxygen below. That deepens and expands oxygen minimum zones, layers in the midwater where O2 is already naturally low. Fish and invertebrates that used to occupy those mid-depth habitats get squeezed between hypoxic waters below and warming, sometimes predator-filled surface waters above. Some species can shift their ranges or evolve better low-oxygen tolerance. Many cannot. As Anoxia expands upward, the habitable band of well-oxygenated water shrinks. Shallow shelf seas, historically the most productive and biodiverse marine habitats, become unstable refuges. Bottom-dwelling communities struggle or vanish. Complex food webs that once included large predators, reef builders, burrowing animals, and suspension feeders simplify into systems dominated by a few hardy, opportunistic species and vast microbial mats. The chemical changes reinforce the biological ones. Under Anoxia, and especially Ozinia, key nutrient cycles change. Phosphorus, for example, tends to be trapped in sediments under oxygenated conditions, but in anoxic settings it can be released back into the water, fueling yet more plankton blooms. That positive feedback, more nutrients, more production, more decay, less oxygen, helps lock basins into a suffocating state. So what do we actually know and what remains uncertain? There is strong multi-proxy evidence that large parts of the late Permian and earliest Triassic oceans experienced severe oxygen loss, including episodes of Ozinia. Many of the most heavily affected regions coincide with where we see the steepest crashes in marine biodiversity, reef belts, continental shelves, and marginal seas. What's still being hashed out is the exact tempo and extent of that suffocation. Some models and datasets argue for relatively rapid onset and near-global deep ocean anoxia during the main extinction pulse, with patchy recovery afterward. Others support a scenario of repeated expansions and retreats of dead zones over a longer interval, possibly tied to pulses of volcanic activity, climate swings and changes in ocean circulation. Either way, the direction of change is clear. As the Permian world heated, its oceans lost their breath. Stratification strengthened. Oxygen vanished from the depths. Poisonous sulfide crept into places it rarely reached before, and the three-dimensional space of the ocean, the volume where complex life could comfortably exist, collapsed. And that chemical suffocation didn't stop with breathing. It set the stage for another, quieter assault on marine life. Not just a shortage of oxygen, but a slow erosion of the very minerals that many creatures used to build their bodies. To see that next layer of the crisis, we have to look at how a CO2-soaked ocean begins to dissolve its own shells. When carbon dioxide dissolves into seawater, it doesn't just disappear. It reacts. A CO2 molecule slips into the water, combines with H2O and becomes carbonic acid. Carbonic acid doesn't last long. It breaks apart into bicarbonate and hydrogen ions. Those extra hydrogen ions are what we measure as acidity. More hydrogen ions, lower pH. But those same hydrogen ions also have a second job. They grab onto carbonate ions, the building blocks that many marine organisms use to make calcium carbonate, the mineral in shells and skeletons. When hydrogen ions tie up carbonate, the water holds less of it in a free, usable form. Chemists talk about carbonate saturation states. It sounds abstract, but for a clam or a coral, it's brutally simple. If saturation is high, crystal growth is easy. If it drops too low, building or maintaining a shell starts to feel like trying to freeze ice cubes in a warm room. You can still do it for a while, but it takes more energy, grows more slowly, and starts to dissolve at the edges. During the end Permian, the Siberian Traps were dumping vast amounts of CO2 into the atmosphere. A big slice of that gas ended up in the ocean. The result was not just warming and stratification. but a long, rolling shock to the carbonate system. We can see traces of this in carbon and boron isotopes, in the way ancient seawater chemistry is recorded in limestones and the tiny shells that survived. There are indications of falling pH and drops in carbonate saturation, especially in shallow, warm waters, the very zones where most marine life and most shell builders were concentrated. In that kind of ocean, calcification becomes a high-risk lifestyle. The late Permian seas were full of animals that used calcium carbonate in a variety of ways. Brachiopods built thick, bivalved shells, many kinds of mollusks, gastropods, bivalves, ammonoids did the same. Reef ecosystems were dominated not by modern corals, but by rugose and tabulate corals, and by sponges that often deposited carbonate frameworks. Algae too, especially calcareous red algae, contributed skeletal material to reefs and carbonate platforms. As carbonate saturation dropped, these groups hit a wall. Fossil records across the Permian Triassic boundary show a stark pattern: heavily calcified, stationary or slow-moving animals, especially those that depended on high saturation, shallow waters, suffered catastrophic losses. Entire reef-building communities vanished. Rugose and tabulate corals, the architectural stars of late Paleozoic reefs, disappear completely. Many large, heavily armoured brachiopods never make it past the boundary. Some groups of gastropods and bivalves plunged in diversity or shrank in size. At the same time, some shell builders did survive, and a few even did relatively well. That contrast is part of how we know acidification wasn't just background noise. Organisms that use different mineral forms of calcium carbonate seem to have had different fates. Aragonite, one common form, is more soluble, easier to dissolve than calcite. In low saturation waters, aragonitic skeletons are at special risk. Many late Permian reef corals used aragonite. They were among the worst hit. Some survivors, by contrast, either used more stable mineralogy, lived in microenvironments with better chemistry, or invested less heavily in thick shells to begin with. Certain thin-shelled bivalves squeaked through. Some echinoderms and crinoids, though heavily calcified, may have retreated to refuges where local conditions stayed favourable. And animals that didn't rely on external carbonate skeletons, soft-bodied worms, some fish, mobile predators that used cartilage or internal ossicles, often fared better. But the real ecological blow wasn't just which species lived or died. It was what happened to reefs themselves. A reef is not just an underwater rock garden. It's a three-dimensional machine for making biodiversity. Reefs create nooks and crannies, cliffs and overhangs, tunnels and caves. They slow currents, trap sediments, and build vertical relief that rises into sunlit water. That structure becomes habitat for thousands of other species, encrusting sponges, filter-feeding bryozoans, small crustaceans, juvenile fish, burrowers in the reef sands, predators that lurk in crevices. The reef framework is the skeleton. The living community is the flesh. Take away the builders, and the skeleton stops growing. Wave energy and storms begin to gnaw the structure down. Bioeroders, boring sponges, grazing urchins, burrowing worms keep working, but new carbonate isn't being added fast enough to compensate. Over time, what was once a towering, complicated reef can collapse into a low, rubble-strewn seafloor. That is exactly what the rock record shows across the Permian Triassic boundary. Rugged, fossil-rich reef facies give way to flat, featureless carbonates or to thin-bedded sediments with little sign of complex framework. For millions of years afterward, Triassic seas are largely without large, wave-resistant reefs. In their place, you get microbialites, layered structures built mainly by mats of microorganisms. Microbial reefs are better than nothing. They provide some structure, some habitat, but they are not equivalent to the sprawling high-rise reef cities of the late Permian. The loss of those carbonate skyscrapers meant the loss of countless ecological niches. It compressed habitats into simpler, flatter seafloors. And acidification wasn't acting alone. Shell builders at the end of the Permian were not facing a single stressor in isolation. They were living in warmer waters, short on oxygen in many regions, subject to fluctuating salinity as climate and runoff changed, and exposed to pulses of volcanic toxins and maybe even metal contamination. Acidification in that context was one more weight added to already overloaded physiological systems. An animal that might cope with slightly lower pH under stable, well-oxygenated conditions may not cope when that same pH drop is combined with chronic heat stress and periodic dips into hypoxia. Energy that could have gone into shell repair, growth, reproduction, or detoxification had to be split among competing demands. At some point, the budget didn't balance. Different models slice the contributions differently. Some emphasize warming and anoxia as the primary killers, with acidification as a major amplifier. Others argue for sharp episodes of acidification, rapid CO2 injections that caused short, intense crises for calcifiers, layered on top of the broader climate and oxygen problems. The exact timing of pH drops relative to extinction peaks is still under active study. But the overall picture that emerges is of a tightly coupled system. Massive CO2 release, warming, ocean stratification, widespread oxygen loss, and a weakened carbonate engine that once kept seawater chemistry buffered and reefs thriving. As shells thinned and reefs crumbled, the oceans didn't just lose species. They lost architecture. They lost the physical scaffolding that supported complex food webs. And in a world already gasping for breath, that collapse of carbonate builders helped lock the seas into a new, simpler, and far more fragile state. If the oceans were being sabotaged from below, the atmosphere was being poisoned from above. The Siberian Traps weren't just CO2 factories. They were chemical weapons labs on a planetary scale. Basaltic magmas, especially when they punch through sedimentary rocks rich in sulfur and halogens, carry more than just carbon. They carry sulfur dioxide, hydrogen sulfide, chlorine, fluorine, and a cocktail of other volatile elements. When that stuff hits the air, the chemistry gets ugly fast. Start with sulfur. When volcanoes eject SO2 high into the atmosphere, it doesn't just drift around as a harmless gas. It reacts with water vapor and oxidants to form tiny droplets and crystals of sulfuric acid, sulfate aerosols. In the modern world, large eruptions that inject SO2 into the stratosphere can cool the planet for a few years by reflecting sunlight back into space. Mount Pinatubo in 1991 did that. It released about 20 million tons of SO2 and cooled global temperatures by about half a degree for a couple of years. Now imagine that same basic process, not as a single eruption, but as pulses of volcanism over tens of thousands of years. Not 20 million tons of SO2, but billions upon billions of tons. Short term, each big pulse could have thrown a reflective veil around the planet, dimming sunlight, disrupting rainfall patterns, chilling some regions even as the long-term CO2 build-up drove warming. Climate models for the end Permian often show this push-pull pattern. Sharp, volcanic winters layered on top of a steadily rising fever. But those sulfate aerosols don't stay aloft forever. Eventually, they fall out, dissolved in raindrops, as dilute sulfuric acid. That's acid rain. On today's Earth, industrial emissions of SO2 and nitrogen oxides produce regional acid rain downwind of power plants. Forests can cope for a while, especially if soils are rich in minerals that neutralize acid. But long enough exposure leaches nutrients, mobilizes toxic metals like aluminum, and damages leaves and fine roots. Lakes and streams turn more acidic, sensitive fish die. Scale that process up, and you get one plausible version of late Permian landscapes. Forests already stressed by heat and drought, now hammered by repeated chemical burn. Acidic rainwater eats away at soil carbonates and feldspars, stripping out calcium and magnesium, flushing pulses of dissolved ions into rivers and coastal seas. That matches evidence of unusually intense weathering at the Permian Triassic boundary, clay-rich horizons, shifts in strontium isotopes, and spikes in elements that are easily washed from land. You don't need acid rain to get strong weathering in a hot, CO2-rich world, but acid rain would have been an efficient amplifier. And sulfur wasn't the only problem falling from the sky. The Siberian Traps magmas tore through thick piles of evaporites, ancient salt deposits, loaded with chlorine and bromine, and through sediments that contained fluorine-bearing minerals. Those halogens and fluorine can be released as gases: hydrogen chloride, hydrogen fluoride, various organohalogens. In sufficient quantities, they become a direct toxic hazard near the vents, corroding lungs and burning vegetation. But there's a more subtle global danger: the ozone layer. Chlorine and bromine compounds that reach the stratosphere are brutally efficient at destroying ozone. Modern CFCs do this. Volcanic halogens can too. Each reactive chlorine atom can catalyze the destruction of tens of thousands of ozone molecules before it's taken out of circulation. Remove enough ozone and more ultraviolet B radiation punches through to the surface. What would that feel like to a late Permian plant? Leaves are solar panels and chemical factories. They're adapted to a certain spectrum and intensity of light. UVB is like turning up the radiation part of that spectrum. It can damage DNA, disrupt photosynthesis, and trigger the production of protective pigments. Plants can cope with some increase. But if the ozone layer thinned significantly, whole forests would have been living under a sterilizing glare. There's a striking line of evidence that something like this might have happened. In rocks right at and just above the Permian Triassic boundary, palynologists, scientists who study pollen and spores, find a peculiar pattern. Many spores show malformed shapes, twisted walls, and thickened, dark outer layers. Some look sunburned. Experimental work on modern plants exposed to elevated UVB produces similar damage features and pigment responses. That has led to the UVB stress hypothesis, that ozone depletion allowed more harmful radiation to reach the surface, injuring plant reproductive tissues. If forest canopies were thinning from heat, drought, and acid rain, and their spores were being fried by excess UV, the regeneration capacity of whole ecosystems could have collapsed. Animals would have felt it too, if less directly. More UV reaching freshwater and shallow marine environments can damage plankton, fish eggs, and amphibian larvae. For terrestrial vertebrates, losing dense plant cover means hotter, more exposed ground surfaces, and fewer shaded refuges, compounding heat stress. So how do we test this toxic sky scenario in rocks that are 252 million years old? Scientists look for multiple lines of evidence. In the microscopic world, they catalogue spores and pollen across the boundary, tallying malformation rates and changes in protective pigments as a proxy for UV stress. They track shifts from forest-type pollen to fern spores that often colonize disturbed ground after die-offs. In the chemical world, they analyze sulfur isotopes. Large, repeated injections of volcanic SO2 into the atmosphere can leave distinctive signatures, a kind of sulfur fingerprint, in sedimentary rocks and minerals like pyrite and gypsum. They also watch for unusual enrichments in elements associated with volcanic or evaporite-derived halogens such as chlorine, bromine, and fluorine, preserved in certain mineral phases or trapped in fluid inclusions. Geologists also study weathering markers in ancient soils, paleosols, and river deposits. Intensified chemical weathering, possibly aided by acid rain, shows up as depleted carbonates, altered clay mineral assemblages, and sharp changes in strontium and lithium isotopes that reflect soil and rock breakdown on land. None of this evidence is a smoking gun on its own. That's part of the challenge. You can get increased weathering from warming and higher CO2 without invoking extreme acid rain. You can get some spore abnormalities from other kinds of stress, not just UV. Volcanic eruptions can release halogens, but how much actually reaches the stratosphere and how long it lingers there depends on eruption style and atmospheric state, things we can only approximate. So when scientists talk about sulfur aerosols, ozone depletion, and acid rain at the end Permian, they tend to use words like plausible, consistent with, and compatible with models, not proven beyond doubt. Different modelling studies give different magnitudes and durations for ozone loss. Some envision modest regional thinning. Others allow for near collapse on a global scale, at least in pulses. What's becoming clear, though, is that the skies above the dying Permian world were not just warmer. They were chemically altered. Forests, soils, and surface waters were operating under a new kind of atmospheric regime, one where rain could sting, sunlight could sterilize, and every metabolic system already pushed to its limits by heat, hypoxia, and food web collapse had one more insult to absorb. And even that wasn't the end of the story. While sulfur and halogens rained from the sky, something far more insidious may have been rising from the seafloor itself, adding a second, delayed carbon bomb to an already spiraling crisis. If the skies were attacking from above, the seafloor may have been quietly loading another weapon from below. To understand it, you have to think of the oceans, not just as water but as a storage system for carbon. A very big, very cold, very unstable storage system. Along many continental margins today, and almost certainly in the late Permian, you find what are called methane hydrates. They're sometimes nicknamed fire ice. They look like ice, but they're actually crystals of water molecules with methane gas trapped inside. They form where three conditions line up: plenty of organic matter buried in sediments, microbes or heat turning that organic matter into methane, and temperatures and pressures just right to lock that methane into a solid. Layered on top of that, in many basins you have thick piles of organic-rich muds and shales. These are the slow cookers of the carbon cycle. Over time, microbes chew up that buried organic material, releasing methane and CO2. Under normal conditions, much of that carbon stays trapped in the sediments or gets slowly leaked out over millions of years. Now picture what happens when you start cranking up the heat. Warmer oceans push the stability zone of methane hydrates back. The depth range where hydrates are comfortable shrinks. At some point they cross a threshold. The hydrates melt, the solid turns back into gas, and methane bubbles out of the sediment into the overlying water. At the same time, warmer, more stagnant waters and expanding anoxia can encourage certain microbes that produce methane to go into overdrive in organic-rich seafloor muds. Either way, you've taken a previously locked-away carbon reservoir and turned it into an active source. This is where the idea of a secondary carbon bomb comes in. For decades, some researchers have argued that the end Permian crisis wasn't just about volcanic CO2 from the Siberian Traps. They suggest there was an additional delayed surge of carbon from destabilized methane hydrates and overcooked organic sediments on continental shelves. The volcanoes light the fuse, the seafloor explodes. How would you see that in rocks 252 million years later? One key clue is in carbon isotopes. Not all carbon atoms are the same. Most are carbon-12. A small fraction are carbon-13. Plants and microbes tend to prefer the lighter isotope, so organic matter, and the methane derived from it is usually depleted in carbon-13 compared to volcanic or mantle-derived CO2. When you measure the ratio of carbon-13 to carbon-12 in marine carbonates or organic matter through the Permian Triassic boundary, you see something striking: a sharp negative carbon isotope excursion. In simple terms, the whole system suddenly looks lighter, more carbon-12 rich. That implies a big injection of isotopically light carbon into the atmosphere-ocean system. Methane fits that bill very well. Biogenic methane in particular can be extremely depleted in carbon-13. Dump enough of it into the atmosphere, let it oxidize to CO2, and the global carbon isotope record will tilt toward lighter values. That's the core of the methane burst story. A large, rapid negative excursion in carbon isotopes, plus evidence of warming and ocean stress, suggests an extra pulse of light carbon on top of volcanic emissions. Destabilized hydrates and hyperactive methane-producing microbes are natural suspects. But as with nearly everything about the Great Dying, the plot isn't so simple. First, there's the issue of source mixing, volcanic CO2, metamorphic decarbonation of limestones and dolomites, combustion of coal beds cooked by intruding magma, oxidation of soil and biomass on land, methane from hydrates, methane from deep thermogenic sources. All of these potential carbon sources have different isotopic signatures, and they can blend. The Siberian Traps didn't just erupt into empty space. They intruded into and baked huge sequences of organic-rich sediments and carbonate rocks. That process alone could release enormous volumes of isotopically light carbon, without needing massive hydrate collapse. Model a mixture of volcanic CO2 plus coal combustion plus decarbonation of organic-rich shales, and you can already reproduce a big chunk of the observed carbon isotope shift. Second, there's diagenesis, the overprinting of the original signal as sediments turn into rock. Carbonates can exchange carbon with pore fluids long after they're deposited. Organic matter can be altered, leached, or overprinted by later microbial activity. Some of the most dramatic isotope shifts might reflect local alteration, not a clean global atmospheric signal. Geochemists are very aware of this. They now compare multiple types of carbon carriers, bulk carbonates, specific carbonate fossils, organic carbon, in multiple basins, trying to tease out what's primary and what's diagenetic noise. The more consistent the pattern across different materials and locations, the more confident they are that it reflects a real global event. Those cross-checks have strengthened the case that a major negative carbon isotope excursion at the Permian Triassic boundary is real and global. But they haven't settled the debate over how much of it is methane. Some models suggest you'd need an almost fantastical release of hydrate methane to explain the full excursion, a volume that might exceed reasonable estimates of how much hydrate could have existed on late Permian continental margins. Others point out that if methane emissions were more modest but sustained, and combined with other light carbon sources like burning coals, you could still get the observed isotopic pattern. Then there's timing. High-resolution studies show that the main negative carbon isotope shift and peak warming coincide closely with major pulses of Siberian Trap volcanism that anchors the primary trigger pretty firmly to the magmas. But there are hints of multi-step behavior, an initial drop, partial recovery, then another plunge. Those steps could reflect feedbacks like methane release, kicking in after the initial volcanic forcing. That's where many researchers are starting to converge. Methane as an amplifier, not the match. In this view, the Siberian Traps load the system with CO2, warm the climate, acidify the oceans, drive anoxia, and start to unravel ecosystems. As bottom waters warm and oxygen disappears, hydrates near the edge of their stability zone begin to dissociate. Microbial communities in organic-rich basins shift toward methane production. Extra pulses of light carbon leak into the system, deepening the carbon isotope excursion and boosting greenhouse forcing just when life is least able to cope. You don't need methane to start the Great Dying, but once the crisis is underway, methane and other seafloor carbon reservoirs may have turned a severe catastrophe into something closer to total system failure. And still, the seafloor had more to offer, as oxygen vanished and strange microbial communities took over. The oceans may have begun exhaling not just methane and CO2, but something even more toxic, hydrogen sulfide, a gas that could have turned the seas themselves into a killing field. To see how that happens, you have to meet one of the strangest ocean states we know of, Oceania. Most of the time, the ocean is layered like a cake. Sunlit, oxygen-rich waters on top, darker, colder, often low-oxygen waters below. Even when the deep ocean is oxygen-poor, the surface usually stays breathable because waves, winds and circulation constantly mix in fresh oxygen from the atmosphere. Euxinic conditions break that pattern. Euxinic means two things at once: no oxygen and lots of hydrogen sulfide dissolved in the water. Hydrogen sulfide is that rotten egg gas, but in high enough concentrations it's not just smelly. It's outright lethal to most complex life, shutting down cellular respiration in a way eerily similar to cyanide. So how do you turn a normal ocean into a hydrogen sulfide factory? Start with expanding Anoxia, the oxygen loss we talked about earlier. Warm the water so it holds less oxygen. Slow or stall the overturning circulation so deep waters aren't resupplied. Dump in nutrients, phosphorus, nitrogen, iron, so algae and bacteria bloom near the surface, then die and sink, using up even more oxygen as they decompose. Once oxygen drops to near zero in bottom waters, a new cast of microbes moves in. One key group are sulfate-reducing bacteria. Seawater is full of sulfate. It's one of the major dissolved ions. These microbes use sulfate the way you and I use oxygen as an electron acceptor in their metabolism. On organic-rich seafloors, they eat buried carbon and breathe sulfate, spitting out hydrogen sulfide as metabolic waste. In a mildly stressed ocean, that hydrogen sulfide gets oxidized, essentially burned back to sulfate before it can accumulate. There's still enough oxygen or other oxidants around to clean it up. But if oxygen has been driven to the floor literally, then the sulfide starts to build. Layer by layer, the bottom waters go from anoxic to eosinic. You now have a toxic brine pooling in the deep, quietly growing, fed by microbial activity and an endless rain of dead plankton. The next question is, can that poison reach the surface? Because deep water killers are bad, but a surface attack is another level. There are a few pathways researchers have proposed. One is simple vertical expansion. If nutrient loading and productivity stay high, more organic matter sinks, more sulfate is reduced, more sulfide is produced. The boundary between sulfide-rich and sulfide-free waters can slowly creep upward. In some modern restricted basins, like parts of the Black Sea, you can see this sharp chemocline, a chemical cliff, separating oxygenated surface waters from sulfide-rich depths just tens of meters below. Now imagine pushing that boundary right up to the surface. Another pathway is physical disturbance. Strong storms, shifts in wind patterns, or changes in ocean circulation can mix up the water column. In a stratified, stressed ocean where sulfide is already lurking not far below the surface, any disruption that brings deep water up or surface water down can blur that boundary. Patches of sulfide-rich water might momentarily break through to the top. There's also the idea of overspill from coastal and shelf environments. In shallow, restricted basins along continental margins, it's easier for bottom waters to go oozinic from top to bottom. If those basins periodically flush into the open ocean, they could belch sulfide-rich water into surface currents that then carry the poison outward. If enough hydrogen sulfide reaches the air-water interface, it doesn't just stay in the ocean. It can outgas into the atmosphere. Model studies suggest that in a world with widespread ozonia, you could get large plumes of hydrogen sulfide venting into the lower atmosphere, at least regionally. At low concentrations, that's a respiratory irritant. At higher levels, it becomes acutely toxic to animals and plants, stripping leaves, damaging lungs, killing outright. At very high levels, it can even start to erode the ozone layer, letting more UV radiation reach the surface and adding yet another layer of stress. This is the hydrogen sulfide hypothesis that during the end Permian crisis, expanding oozinic waters periodically reached shallow depths, venting H2S into coastal seas and perhaps the atmosphere, turning already stressed ecosystems into killing zones. For that to work, you need not just anoxic water, but the right kind of microbial machine. Under high nutrient loads and low oxygen, microbial communities reorganize. Photosynthetic algae bloom at the surface, feeding heterotrophic bacteria below. As oxygen disappears, other microbes take over key steps of the sulfur and nitrogen cycles. Green and purple sulfur bacteria, organisms that can use hydrogen sulfide as an electron donor for photosynthesis, can form dense layers at the boundary between sulfide-rich and oxygen-rich waters, creating a kind of microbial sandwich. Oxygenated water on top, sulfide-rich water below, a photosynthetic microbial mat in between. In that setup, biology doesn't just respond to environmental collapse. It reinforces it. The blooms pump more organic matter into the system. More organic matter means more food for sulfate reservoirs on the seafloor. More sulfate reduction means more hydrogen sulfide. Sulfide-tolerant microbes thrive and spread, outcompeting organisms that need oxygen. The ocean's chemistry and its biology lock into a new toxic feedback loop. Do we have direct evidence that this happened at the end of the Permian? We can't bottle Permian seawater, but we can read its chemical ghost in sediments. Certain forms of sulfur and iron in rocks, what geochemists call redox-sensitive minerals, carry signatures of oozinic conditions. Organic molecules or biomarkers from sulfur-loving bacteria show up in some Permian Triassic boundary rocks, hinting that green and purple sulfur bacteria were common in the photic zone, the sunlit upper layer of the ocean. That implies sulfide was present surprisingly close to the surface. In some sections you see spikes in these biomarkers right when other lines of evidence, carbon isotopes, fossil collapses, signs of anoxia, suggest peak crisis. That's exactly what you'd expect if microbial blooms and expanding oozinia were part of the kill mechanism. But there are caveats. Not all basins show the same signals. Some rocks that formed in deeper offshore settings look more like classic anoxia than full-blown oozinia. Biomarkers can move around in sediments, and some can be produced by multiple types of organisms, not just the dramatic sulfur bacteria we like to imagine. And turning local or regional oozinia into a global atmospheric hydrogen sulfide event requires a lot of scaling up, and some of those scaling steps are still debated. Some researchers see H2S as a central killer, perhaps even spilling onto land and helping drive terrestrial extinctions. Others think oozinia was more patchy, one regional horror among many, deadly in some basins, but not the universal death shroud. In that view, hydrogen sulfide is part of the story, but not the whole story. What's hard to escape is the broader pattern. As ecosystems collapsed, Microbes stepped into the vacuum and rewrote the rules of chemistry. Under volcanic forcing and climate stress, the oceans didn't just quietly fade. They flipped into a new biological regime where simple organisms, bacteria and archaea, became major drivers of planetary scale feedbacks. They amplified warming, deepened anoxia, and in some places probably turned the water itself into a toxic weapon. Life, in other words, helped finish the job that geology started. And on land, something similar may have been happening. As forests withered and soils eroded, the very structure of rivers and landscapes began to change, leaving a record of chaos that we can still see written in stone. On land, the story starts with something deceptively simple. Trees trying to keep their cool in a world that's running a fever. Plants can't move to the shade. They're stuck where they sprout, dealing with whatever the sky decides to throw at them. And for Permian forests, the sky was becoming an enemy. Every plant has a thermal comfort zone. Above a certain temperature, photosynthesis starts to falter. Enzymes misfire. Cell membranes get leaky. Stomata, the tiny pores on leaves that let in CO2 and release water, become a life and death gamble. Stay open and the plant can keep feeding itself, but it loses precious water. Slam them shut to conserve moisture, and photosynthesis starves. Now put that plant in an atmosphere thick with CO2, under a sun beating down on a supercontinent, mostly surrounded by warm seas. Climate models of late Permian Pangaea suggest vast interior regions were already hot and seasonally dry even before the crisis peaked. Add rapid greenhouse warming on top of that, and you push many plants right up against their physiological limits. Longer, hotter summers, more frequent droughts, higher evaporative demand, meaning the air is constantly trying to suck water out of leaves and soils. Under those conditions, forests don't just quietly thin. They become stressed systems primed for failure. Water stress makes plants vulnerable. Roots can't reach enough moisture. Xylem, the microscopic pipes that pull water up from the ground, start to cavitate. Tiny air bubbles form and spread, breaking the hydraulic connection from soil to leaf. Once that system is badly damaged, the plant is basically done, even if rain eventually returns. Heat also changes how plants burn. Moist, healthy forests can resist fire. Dead, desiccated forests are kindling. The hotter and drier the climate, the longer the fire season, the more easily lightning or lava-heated air, or even spontaneous peat ignition can set vast areas ablaze. Around the Permian Triassic boundary, sedimentary rocks record a spike in charcoal, microscopic burnt plant fragments that are the geological fingerprints of wildfire. In some regions, charcoal becomes far more abundant right as other crisis signals intensify. To many researchers, that looks like a classic feedback. Warming and drought stress plants. Dead biomass accumulates, fires become more frequent and more intense, which in turn clear forests and dump even more CO2 and soot into the atmosphere. You start with a forest. You end with a landscape that looks more like a charred, eroding scrubland. This is where the so-called coal gap comes in. Before the crisis, much of Earth's coal was being laid down in lush, swampy environments, forests and wetlands where plant material piled up faster than it decayed. Buried and compressed over millions of years, that organic mush turns into coal seams. Then right around the end, Permian extinction, something strange happens in the rock record. For a long stretch of early Triassic time, economically significant coal deposits pretty much vanish in most places. It's as if someone turned off the world's peat-forming machine. This absence is what geologists call the coal gap. There are different ways to interpret it. One is straightforward. The kinds of dense, waterlogged forests and peatlands that generate lots of coal simply collapsed. The climate in many regions became too hot, too dry, too unstable for those ecosystems to persist. Instead of thick mats of decaying plant matter in soggy basins, you get thin, discontinuous plant horizons, soils stripped off by erosion, and sediments full of sand and mud rather than organic mush. Another layer to the story is ecological. Coal-forming environments need not just plants, but the right kind of plant communities: large woody trees, dense undergrowth, stable water tables. If mass extinction wipes out the dominant tree groups and replaces them with low, scrubby vegetation better suited to heat and drought, peat production can plummet even if plants are technically still there. Not everyone agrees the coal gap is global or absolute. Some regions do show minor coal or coal-like deposits in the early Triassic, and new discoveries occasionally tweak the timing. But the broad pattern is hard to ignore. Relative to before and after, the early Triassic looks like a world where large, long-lived coal-making forests had nearly disappeared. Strip away the forests, and the land stops behaving the way it used to. Roots are more than anchors. They're the stitching that holds soil to slopes and riverbanks. Leaf litter is a sponge and a shield, protecting soil from the direct impact of raindrops, slowing down runoff, feeding the organisms that build structure into the ground. When that cover goes, the next big rain doesn't soak in. It scours. In many late Permian to early Triassic rock sequences, you see exactly that kind of transition. Older layers show well-developed paleosols, ancient soils, with clear horizons, root traces, and subtle layering. Overlying those, you start to see coarser, more chaotic deposits, thick sheets of sand and gravel, stacked channel fills, and mudstones crammed with angular sediments washed off bare slopes. Rivers that once meandered across vegetated floodplains, dropping fine silts and building stable banks, shift toward more braided, flashy systems, multiple shallow channels wandering through wide, unstable bars of sand and gravel. That's the sedimentary signature of a landscape that's been deforested and destabilized. The loss of plants doesn't just affect rocks and rivers. It punches straight through the food web. Permian land ecosystems were built on plants the same way modern ones are. Giant club mosses, seed ferns, conifers, and other groups formed the base. Herbivores from small burrowing synapsids to large cow-sized or even rhino-sized plant-eaters depended on that green foundation. Carnivores depended on the herbivores. When forests break down, the first to feel it are the specialists. Animals adapted to particular types of foliage, bark, or seeds. If your jaw, teeth, and gut are tuned to chew tough, fibrous fronds in a cool, damp understory, you're in trouble in a hot, fire-prone, open scrubland. Fossils suggest that many large herbivores didn't make it through. Their decline shows up in the record as a drop in diversity and body size, and eventually as gaps where whole groups disappear altogether. Predators follow. Apex carnivores need large, stable prey populations. As herbivores crash, big predators face starvation or are forced into desperate, less efficient ways of life, scavenging, targeting smaller prey, competing with each other more directly. Some lineages shrink in size, others vanish. Smaller, more generalist animals seem to have had a better shot. Creatures that could eat seeds, roots, insects, carrion, basically anything they could find, stand a better chance in a world where the old menu has been ripped up. But even they were navigating a landscape hammered by heat, drought, fire, and the constant reshaping of rivers and soils. And this wasn't the same everywhere, all at once. Pangaea was huge. Climate models and fossil data both point to strong geographic variability. Some high-latitude regions may have retained patchy, cooler refuges where forests hung on longer. Coastal zones influenced by moist onshore winds might have been buffered, at least for a while, from the worst interior heat and dryness. In some basins, Plant fossils show a more gradual turnover rather than an abrupt wipeout. In other areas, especially the continental interiors and regions downwind of intense volcanic activity, the change looks sharper. Charcoal spikes, plant diversity plummets, coal formation stops, and river systems reorganize within a relatively narrow slice of rock. Think of the end Permian land crisis not as a single uniform event, but as a mosaic of regional disasters unfolding on slightly different schedules. Some forests die back slowly, then cross a tipping point and vanish. Others burn, regrow in simplified form, and then fail again as the climate ratchets hotter and drier. What ties all these pieces together is the direction of change. Under relentless volcanic forcing and rising greenhouse gases, landscapes trend toward the same grim endpoints. Fewer trees, more open and degraded ground, more fire, more erosion, simpler food webs dominated by survivors that can tolerate extremes. By the time the oceans have flipped into anoxic and even eusinic states, much of the land surface has already been stripped, cooked, burned, or destabilized. The green fabric that once covered Pangaea has been torn, and the threads that connected climate, vegetation, soils, rivers, and animals are fraying. In the next step of the story, you can actually see that unravelling written in the rocks themselves, entire river systems changing character as the forests that once shaped them disappear. When geologists say river systems reorganized at the end of the Permian, that sounds almost polite. The rocks tell a much harsher story. Under stable climates with healthy vegetation, rivers tend to behave in predictable ways. Meandering channels carve lazy S-curves across their floodplains, hemmed in by cohesive banks, held together by roots. They overflow now and then, lay down thin blankets of mud, build soils, feed wetlands. Over thousands of years, this creates a layered archive, fine silts, subtle soil horizons, plant roots piercing down into the sediment. As climate swings harder and plants vanish, that balance breaks. Without deep, interlocking root systems, river banks lose their tensile strength. Leaf litter and ground cover disappear, so rain hits bare soil directly, dislodging grains and turning gentle slopes into source areas for debris. At the same time, hotter temperatures and more erratic rainfall mean storms become the main delivery mechanism for water, a lot of it all at once. The rivers respond by changing personality. In many late Permian, early Triassic basins, you see a clear shift from meandering to braided river styles. Instead of one dominant, sinuous channel, you get anastomosing threads of water weaving through broad belts of loose gravel and sand. Channels split and rejoin. Bars migrate quickly, banks are low, easily overrun. The sediments match that picture. Thick, laterally extensive sheets of coarse material, stacked one atop another, with only thin or poorly developed soils in between. These packages sometimes contain megafans or unusually thick channel fills, evidence of powerful, short-lived floods ripping through destabilized catchments. It's as if the landscape went from being stitched together to being shredded, and the rivers were carrying away the pieces. In places like the Karoo Basin of South Africa, the Sydney and Bowen Basins in Australia, parts of European Russia, and sections of North China, geologists have walked through this transition bed by bed. They see late Permian successions with mature paleosols, clear rooting structures and well-behaved river deposits. Then, within meters of vertical section, representing what might be tens of thousands of years, maybe less, those features give way to more chaotic, high-energy fascias. One layer you're standing in the quiet floodplain of a vegetated world. A few steps up, you're in the sedimentary footprint of a stripped, flash flood-prone landscape. These onshore boundary sections are the terrestrial analogues of the famous marine records in places like Meishan, China. They bracket the extinction horizon on land with a suite of clues. charcoal spikes, changes in fossil plants and vertebrates, and this dramatic retooling of river behaviour. In some basins, the end Permian boundary is marked by thick, reddish mudstones, oxidised floodplain deposits, overlain abruptly by coarse channelized sands and gravels. In others, you see stacked paleosols in the Permian replaced by weakly developed or even reworked soils above, suggesting frequent erosion before profiles could mature. Sometimes there are horizons packed with reworked plant debris and vertebrate bones concentrated by violent flows. All of that points to increased erosion and sediment pulses hammering downstream environments. What drives that kind of instability at continental scale? Vegetation loss is a big part of it, but the atmosphere above those bare slopes was not passive. Volcanic ash and sulfate aerosols from the Siberian Traps eruptions would have injected enormous amounts of particles into the stratosphere and troposphere. Short term, those aerosols can cool the surface and alter temperature gradients, changing wind patterns and storm tracks. Over longer intervals, as greenhouse gases accumulate, you get net warming, but superimposed on a more chaotic hydrological cycle. Some climate models suggest that under high CO2 and large aerosol loads, monsoon systems can intensify or migrate. Regions that once had relatively gentle, predictable rainfall may have shifted into regimes of long dry spells punctuated by extreme downpours. That's exactly the recipe for flashier rivers. Soils dry and crack, then a single event sends torrents of water sheeting off the surface loaded with sediment. Ash itself can play a double role. A thin blanket of ash can initially seal soils, increase runoff, and smother vegetation. Finer ash mixed into the water column can change how rivers deposit their loads, sometimes creating unstable bars that are easily remobilized in the next flood. Over time, chemical weathering of volcanic material also releases nutrients and ions, potentially impacting lakes and lowland environments. So when you see those stacks of coarse, rapidly emplaced sediments in early Triassic river systems, you're probably looking at the combined signal of a baked, deforested landscape and an atmosphere periodically jolted by volcanic injections. But tying all these onshore stories into a single global narrative is tricky. In the oceans, you have continuous sedimentation in many places, rich in microfossils and chemical traces. You can line up carbon isotope spikes, extinction horizons, and volcanic markers across multiple basins with reasonable confidence. On land, the record is patchier. Erosion removes pieces. Non-deposition leaves gaps. Rivers migrate, cutting away their own history. Dating terrestrial sections precisely is also harder. You often lack the abundant marine fossils that make biostratigraphy so powerful. Instead, you rely on sporadic volcanic ash beds for radiometric dates, vertebrate and plant assemblages that can be correlated only within broad windows, and geochemical tie-ins to nearby marine sections where possible. That means when geologists compare a river shift in South Africa with one in Russia or China, they're usually working with uncertainties of tens to hundreds of thousands of years. Some sequences show apparently abrupt changes right at the extinction horizon. Others show more gradual transitions smeared out over thicker packages of rock. Is that because the environmental shock hit different regions at slightly different times and intensities? Or is it mostly an artifact of how incomplete and time-compressed the terrestrial record is? Most researchers think it's a bit of both. The broad pattern, more erosion, more sediment, more braided and unstable rivers near the Permian Triassic boundary, shows up on multiple continents. That's hard to attribute to coincidence, but nailing down exactly how those shifts line up with pulses of volcanism, atmospheric change, and biological collapse is still an active area of work. What's clear is this. By the dawn of the Triassic, Earth's rivers were no longer quietly meandering through lush, peat-forming lowlands. They were feral, overloaded and restless, carving and recarving their floodplains over landscapes that had lost much of their living armour. And as those rivers tore at the land, they became part of a larger cascading system, moving nutrients, carbon, and toxins from the continents into the already stressed seas, helping to knit the terrestrial catastrophe to the marine one in a single planetary crisis. When you hear that 80 to 90% of species vanished, it's tempting to imagine the great dying as a blind scythe swinging at random. It wasn't. Extinction at the end of the Permian was brutal. But it was also selective. Certain body plans, metabolisms and lifestyles bought you a ticket through the bottleneck. Others were like signing your own death warrant. In the oceans, the pattern is stark. Animals that depended on high oxygen levels, stable conditions and calcium carbonate skeletons were hammered hardest. Reef-building organisms, rugose and tabulate corals, many sponges, and the bizarre reef factories of the Permian like calcifying algae and microbial sponge consortia largely crashed. Whole reef ecosystems, which had been architectural centerpieces of shallow seas for hundreds of millions of years, disappeared so thoroughly that it took 10 to 15 million years for something comparable to re-establish. Trilobites, already declining, hit their final wall. They never make it past the boundary. Conodonts, those tiny tooth-bearing eel-like vertebrates that had ridden out previous crises, lost many lineages. Large, heavily calcified brachiopods, and some bivalves do especially poorly. Many groups with thick, heavily mineralized shells or skeletons seem to have been caught in a perfect storm. Acidified waters that ate at their carbonate, low oxygen that stressed their metabolisms, and hot, sluggish seas that erased their thermal comfort zones. By contrast, the survivors often look modest. Thin-shelled bivalves. Small, simple gastropods, opportunistic omnivores. Organisms that could tolerate wide swings in temperature and oxygen, that didn't invest heavily in massive carbonate skeletons, and that could reproduce quickly, sometimes with larvae that dispersed widely. Some invertebrates that lived in burrows within the sediment, where oxygen was often scarce even in good times, were pre-adapted to the widespread anoxia of the crisis. If your ancestors had already solved the problem of living on the edge of suffocation, the end Permian oceans, awful as they were a bit less of a shock. Then there are the refuges. Even in a global catastrophe, conditions don't deteriorate everywhere in exactly the same way at exactly the same time. Some parts of the ocean column, some latitudes, some microhabitats became relative safe zones, refugia in a collapsing world. Cooler, higher latitude waters may have stayed below lethal temperature thresholds for longer. Deeper settings, away from the most extreme coastal runoff and temperature spikes, might have offered more stable chemistries, at least episodically. There's evidence that some lineages contracted from broad, panthalastic distributions to narrow bands along continental margins or around upwelling zones where oxygen and nutrients still cycled. Think of marine life pulling back from a vast empire to a few fortified strongholds. Many post-extinction survivors show exactly this pattern in the fossil record. Broad distributions in the Permian, then sudden restriction to a handful of basins in the earliest Triassic, then slow, halting re-expansion millions of years later. Survival didn't mean cruising through unscathed. It meant being squeezed into tiny marginal spaces with genetic and ecological diversity shaved down to the bone. On land, the selectivity looks different but is driven by the same basic logic. Who can cope with heat, drought, and chaos? The towering arborescent lycopsids and diverse seed fern forests of the late Permian were shredded. Many groups of large woody plants with complex moisture-dependent life cycles vanish or drop to tiny remnants. In their place you see spikes of disaster taxa, hardy, fast reproducing plants that can colonize stripped soils and tolerate extremes. Glossopteris dominated floras in Gondwana collapse. Instead, you get assemblages dominated by things like peltosperm seed ferns and later conifers that could handle drier, more seasonal climates. Among vertebrates, big, specialized top predators do badly. Many large therapsids, those mammal-like reptiles that had once ruled Permian ecosystems, either vanish entirely or shrink back to a few lineages. The record is full of Lazarus taxa, groups that disappear from the rocks for a while, then reappear in the Triassic, likely because their populations had been reduced to tiny, geographically limited refuges too small to be captured consistently in the fossil record. By contrast, small generalist, often burrowing animals fare better. Creatures that could hide underground from temperature extremes, that didn't need vast, lush hunting territories, that could eat a wide range of foods. They show up disproportionately among the survivors. Some early archosaur relatives, ancestors of the later Triassic dynasties of crocodiles and dinosaurs, skate through this window. So do certain cynodonts, the line that will eventually give rise to mammals. Again, refugia matter. Cooler uplands, shaded valley bottoms, north-facing slopes, wetter microhabitats near springs or groundwater seeps. These become terrestrial equivalents of deep water sanctuaries. Local patches where temperatures were a bit lower, humidity a bit higher, fires a bit less frequent, could host remnant populations long after surrounding lowlands had turned into semi-barren dust bowls. If you look at the earliest Triassic terrestrial record, you don't see a flourishing, diverse biosphere. You see a world of ecological bottlenecks, low-diversity faunas dominated by a few tough, weedy species. In many basins there's even a fungal spike, a brief dominance of fungal spores interpreted by some as decomposers feasting on vast amounts of dead plant material, or simply as opportunists taking advantage of open, nutrient-rich substrates. This is what survival really looked like. It wasn't a clean line between winners and losers, with some groups serenely sailing through while others dropped off a cliff. It was a long, grinding filter. Lineages staggered, shrank, vanished from view, reappeared, retreated into scattered refuges, then, if they were very lucky, began the glacially slow process of recovery. And that recovery was shaped, at every step, by these patterns of selectivity. Who had made it through, in what numbers, in what places, with what traits, would determine how ecosystems reassembled and which branches of the tree of life would be given a second chance to radiate. But selectivity alone doesn't explain the scale of the loss. For that, you have to look at how all these stresses link together, how rivers, oceans, atmosphere and biology combined into a cascading system that could turn even small nudges into planetary catastrophe. To understand that cascade, start at what seems like a simple beginning, magma. The Siberian Traps eruptions pump enormous amounts of CO2 and other gases into the atmosphere over tens to hundreds of thousands of years. Not a single apocalyptic blast, but pulses, waves, like a fever that keeps spiking and never fully breaks. More CO2 means a stronger greenhouse effect. Global temperatures rise by a few degrees at first, then more. On a human scale, that might feel like the difference between a cool spring and a blazing summer. On a planetary scale, it changes how the entire climate engine runs. Warm the surface ocean relative to the deep, and you set up stronger stratification. The upper layer becomes lighter, hotter, and more buoyant. It doesn't want to mix. Vertical overturning, the slow, crucial conveyor belt that brings oxygen-rich surface water down and returns nutrient-rich deep water up, starts to stall. Less mixing means less oxygen reaching the deep ocean. Respiration and decay keep using up what's already there. Slowly, then faster, large volumes of the seafloor slip into hypoxia and then anoxia. Now the chemistry starts to flip. Under oxygen-poor conditions, microbes change their game. Instead of using oxygen to break down organic matter, they turn to other electron acceptors, nitrate, sulfate, even carbon dioxide, producing things like ammonium, methane, and hydrogen sulfide. Iron and phosphorus locked in sediments are released back into the water. Nutrients that were once buried get recycled into the overlying ocean. On the surface, the extra phosphorus and nitrogen can fuel blooms of primary producers, algae, cyanobacteria, maybe even those weird sulfur-loving microbes that some models invoke. Blooms mean more organic material raining down into the deep, where it decays and consumes yet more oxygen. You've just closed a loop: warming stratification, anoxia nutrient release, more productivity, more sinking organic matter, deeper anoxia. Each turn of the wheel makes the next turn easier. At the same time, the carbon cycle is trying to respond. Add CO2 and you don't just warm the planet, you also speed up some of the processes that pull CO2 back out. Warmer climates can intensify the hydrological cycle. More evaporation, more rainfall in some regions, stronger weathering of rocks on land. As rain and weak carbonic acid attack silicate minerals, they release ions that rivers carry to the sea, where they help form carbonate minerals that lock carbon away in sediments. Silicate weathering is Earth's long-term thermostat. Crank up the heat, and given enough time, weathering should ramp up and draw CO2 back down. But during the Great Dying, a lot conspired to short-circuit that safety valve. Deforested, fire-scorched landscapes didn't hold soils well. Intense but sporadic rains could strip hillsides bare, delivering pulses of mud and nutrients rather than slow, steady chemical weathering. Acid rain from volcanic sulfur and halogens may have further altered surface reactions. In some basins, the sedimentary record shows chaotic, erosion-dominated deposits, a sign that landscapes were being physically torn apart more than they were quietly chemically dissolved. In the ocean, anoxia changes the fate of carbon. In some situations, low oxygen helps preserve organic matter that would otherwise be oxidized, increasing organic carbon burial and pulling CO2 out of the atmosphere. In others, especially if anoxia is patchy and overlain by highly productive surface waters, much of that sinking organic matter is still remineralized, turned back into CO2 or methane at depth, then slowly leaks out to rejoin the atmosphere-ocean reservoir. Methane is its own wild card. Warming can destabilize methane hydrates in seafloor sediments and permafrost-like settings, releasing CH4 into the water column and atmosphere. Methane is a potent greenhouse gas on short timescales. But oxidize it either in the ocean or the air, and you convert it to CO2 and consume oxygen in the process. So a methane pulse can simultaneously boost warming and nibble away at remaining oxygen. Weathering, organic burial, methane release, oxidation, all these levers were being yanked at once. Some acted to damp the crisis, others to amplify it, and their relative strengths are still debated. Different models give different answers about how fast weathering could respond, how much organic carbon was buried versus burned back to CO2, how big any methane secondary bomb might have been. What's clear is that the system didn't just slide smoothly back to normal, it flipped. Ecologists talk about alternative stable states. Picture a ball in a landscape of hills and valleys. In one valley, you have a well-oxygenated, moderately warm ocean with diverse food webs and carbonate-secreting reefs. In another valley, you have hot, stratified, oxygen-poor seas dominated by microbial mats, opportunistic invertebrates, and chemical cycles that recycle nutrients but don't easily rebuild complex communities. You can push the ball around within a valley. Short warm spells, small eruptions, regional anoxia. And when the push stops, It rolls back to its familiar resting place. But push hard enough or long enough, and the ball can cross a ridge and fall into a different valley altogether. Once there, the same feedbacks that used to stabilize the old state now stabilize the new one. At the end of the Permian, multiple moderate stresses stacked in the same direction. Volcanic CO2-raised temperatures, that warming stratified oceans and stressed land ecosystems, dying forests and soils pumped nutrients and carbon into rivers, feeding coastal blooms and coastal anoxia. Deep ocean anoxia and Ozone released more nutrients and maybe toxic hydrogen sulfide, killing off sensitive organisms and favouring hardy microbes. Reef builders and complex food webs collapsed, removing biological structures that once buffered local environments. No single factor taken alone has to be extreme to be dangerous. A bit more CO2, a bit more nutrient runoff, a bit more stratification, a bit less oxygen. But when each of those nudges strengthens the others, you no longer get a bad year or a warm millennium. You get a planet that has reorganized its own operating rules. And crucially, the same cascades that drive collapse also shape recovery. Once reefs are gone, it's harder to rebuild carbonate platforms that help stabilize shorelines. Once soils are stripped and forests fragmented, you change weathering patterns and atmospheric dust loads. Once deep waters are persistently anoxic, they keep leaking out nutrients and toxins that favour simple, fast-cycling ecosystems over complex, slow-growing ones. So when we talk about the Great Dying, we're not just cataloguing dead trilobites and scorched forests. We're looking at an Earth system that was knocked out of one stable configuration and trapped, for millions of years, in another. Of course, volcanism wasn't the only proposed shove. Some researchers have pointed to other triggers: coal-rich rocks combusted by intruding magma, possible impacts and more as potential accelerants in this cascade. To see how they might fit into the story, we have to look at the alternative culprits that have been put on trial alongside the Siberian Traps. If you're going to accuse something of nearly sterilizing the planet, you'd better be sure you've got the right culprit. So, over the last few decades, scientists have gone full detective mode on the Great Dying, testing not just the obvious suspect, massive volcanism, but every other plausible accomplice they can think of. One of the first questions, especially in the post-dinosaur impact era, was simple: did something big hit us? An asteroid or comet slamming into Earth can do a lot of what we see at the end. Permian, inject dust and aerosols, destabilize climate, ignite fires, acidify oceans. So if a Chicxulub-style impact triggered the Great Dying, what would we expect to find? You'd look for the classic forensic kit: a spike in iridium, a metal more common in meteorites than in Earth's crust, shocked quartz, tiny sand grains whose crystal structure has been deformed by extreme pressures, microtectites, glassy spherules formed when rocks are vaporized and then condense out of the fireball, maybe even a crater of roughly the right age and size. There are hints, but they're messy. Some end Permian sections show small iridium enrichments, but nothing like the sharp global spike at the end of the Cretaceous. A few sites have reported odd microspherules or structures that some researchers have interpreted as impact debris, others as volcanic products or diagenetic artifacts. There are candidate craters and disturbed structures on older continental crust that have been tentatively linked to the Permian Triassic boundary, but dating them precisely has proven extremely difficult. Many turn out to be too old, too young, or too ambiguous. Instead of a clean global impact fingerprint, we get a patchwork of maybes and could-be's, enough to keep the idea on the table as a possible local shock or a smaller contributing event, but not enough to make an asteroid the main driver in most current models. If there was an impact, it looks less like the gunshot that killed the dinosaurs and more like someone kicking a body that was already collapsing. A different alternative culprit turns out to be hiding in plain sight, right under the Siberian Traps, the rocks the magma intruded into. When hot magma forces its way into thick piles of sedimentary rock, it doesn't just sit there politely. It bakes the surrounding layers. This is contact metamorphism, thermal alteration of rocks simply because they're in contact with something very hot. If those sediments are rich in carbon, coal beds, organic-laden shales, bituminous limestones, that baking can turn them into giant industrial ovens. You're effectively running hundreds of thousands of square kilometers of underground coke furnaces for as long as the intrusions stay hot. Organic matter gets cooked, broken down, and released as gases: CO2, methane, maybe carbon monoxide, and a cocktail of other volatiles. This magma meets carbon-rich rock idea is one of the most powerful elaborations of the Siberian Traps hypothesis. It says, don't just count what comes out of the volcanoes at the surface. Count what happens when all that magma silently invades the crust. The evidence here is more substantial. In Siberia, we can actually map huge sill complexes, tabular intrusions that snake through thick sequences of Permian coal and evaporites. Around these intrusions you see baked zones where coal has been devolatilized, carbonates decarbonated, sulfur-bearing rocks turned into new mineral assemblages. Geochemical studies of end Permian sediments show carbon isotope excursions that are hard to explain with volcanic CO2 alone, but easier to match if you add in a pulse of isotopically light carbon from baked organic matter. Some models suggest that the total greenhouse gases released by contact metamorphism of coal, shales and carbonates in Siberia could rival or even exceed the direct volcanic outgassing. In that view, the eruption is the match, but the carbon-rich crust is the bonfire. Closely related is a more dramatic idea, not just slow baking but wholesale combustion of coal seams and hydrocarbons set alight by intruding magma. Think of vast underground coal fires, like the ones that burn for decades today in abandoned mines, but scaled up to continental dimensions and geological timescales. If magma intersects coal beds near the surface, you can ignite them. Once burning, those seams can propagate along the coal horizon, venting CO2, methane, soot and toxic gases to the atmosphere for as long as the fuel lasts. What would be the signatures of that kind of combustion? You'd expect to see inertinate, fossil charcoal, and burned organic fragments increasing in sediments across the boundary. You might see black carbon spikes, polycyclic aromatic hydrocarbons, PAHs, and specific isotopic fingerprints of burned terrestrial plants and coals. You'd also expect the carbon isotope record to plunge sharply toward lighter values reflecting the injection of biologically processed carbon into the atmosphere-ocean system. We do see some of this. There are intervals with abundant charcoal, elevated PAHs, and dramatic negative carbon isotope excursions. Some coal seams in Siberia show evidence of partial burning and alteration, but separating coal burned in place by magma from massive wildfires in devastated forests in the rock record isn't trivial. Both can produce charcoal, both can leave similar organic residues. The two processes may have been happening together, each feeding the other. So how do these alternative culprits stack up against the volcanism-centered model? In practice, the debates are less volcanoes or something else, and more how many amplifiers were running at once, and which was the loudest. The Siberian Traps eruptions provide an obvious, well-dated, long-lasting flux of heat and gases. That's the anchor. Contact metamorphism of coal and carbonates piggybacks on that same magmatic system, potentially boosting greenhouse gas emissions by a factor of several. Coal seam combustion might add sharp, intense pulses of additional carbon and soot. A minor impact, if it happened, could jolt climate or ecosystems already under stress. maybe tipping a marginal system over a threshold. The current centre of gravity in the field still puts large igneous province volcanism, the Siberian Traps and their subsurface plumbing, as the dominant driver of the Great Dying. It's the one mechanism we know for sure was operating at the right time, in the right place, with the right scale of energy and carbon release. But within that framework, there's plenty of room for complexity. Some models can't reproduce the full magnitude and speed of the observed warming and carbon cycle disruption with surface volcanic CO2 alone. Adding contact metamorphism and coal combustion helps bridge that gap. Other studies argue that you can get most of the way there with sustained volcanism, interacting with sensitive Earth system feedbacks, without needing exotic add-ons. And that's the deeper lesson. Mass extinctions aren't courtroom dramas with a single smoking gun. They're more like multi-car pile-ups in heavy fog. One driver slams on the brakes. That's your large igneous province. But then visibility drops. The road ices over. Other drivers overreact or can't stop in time. Each additional impact makes the whole scene worse. For the end Permian, the fog is the state of the Earth system itself, already primed by geography, climate, and biology to react strongly to a big shove. Volcanism was almost certainly that shove. Contact metamorphism, coal burning, perhaps even a modest impact may have added their own brutal pushes. What matters for us is that, however you apportion the blame, the outcome was the same. A cascade of feedbacks that didn't stop when the initial forcing did. To see just how long that cascade kept Earth trapped in a nightmare state, we have to follow the planet into the early Triassic, a world that looked less like a recovery and more like a prolonged aftermath. So the eruptions taper, the worst of the carbon flood slows, and you might expect life to bounce back. In most nature documentaries, this is the part where the triumphant music swells and green shoots push through the ashes. But in the early Triassic, the camera would pan out and almost nothing happens. For millions of years after the official end of the extinction interval, Earth doesn't snap back to lush Permian forests and bustling reefs. Instead, it stalls in something much stranger, a simplified, low-diversity dead zone world, where ecosystems look like they've been reset to the tutorial level and then left there. You see it everywhere in the fossil record. Before the crisis, late Permian seas were layered with complexity. Coral-like organisms, sponges, brachiopods, ammonoids, fishes, invertebrates living on, in, and above the seafloor. Predator-prey networks stacked in multiple tiers. Niche on niche. Cross the boundary into the early Triassic, and that whole tower collapses. In many marine sections, diverse bottom communities are replaced by a small handful of hardy species that seem almost purpose-built for catastrophe. These are disaster taxa, organisms that thrive when everything else has been knocked out. One classic example is the bivalve Chlorea. In some early Triassic rocks, Chlorea shells are practically the only thing you find, jammed together in monotonous layers that stretch for meters. Another is the so-called microbial world. Instead of coral reefs, you get vast mats and mounds built by microbial communities, carbonate structures that look in thin section like somebody smeared bacterial scum across the seafloor and then turned it to stone. On land, it's a similar story. The intricate late Permian forests with deep root systems, layered canopies, diverse undergrowth, and specialized herbivores are gone. Many early Triassic plant beds are dominated by a few weedy, fast-growing forms like Lycopsids and other spore-bearing pioneers that excel at colonizing disturbed ground. Thick, mature soils give way to thin, poorly developed layers. River deposits show more bare, eroding landscapes, fewer signs of stable vegetated floodplains. In both realms the pattern is the same. Low diversity, high dominance by a few tough generalists, communities that look simple and, more importantly, feel fragile. Ecologists today would call these unstable assemblages. Knock out one or two key players, and there isn't much redundancy left to take the hit. Why didn't life just rebuild the complexity it had before? Part of the answer is that recovery isn't an on-off switch. Even if the main kill mechanism, say the peak rate of carbon release from Siberia, slows down, the Earth system doesn't instantly revert to its old state. There's inertia in the oceans and atmosphere, lags in the carbon cycle, and a whole suite of feedbacks that take time to unwind. You can think of it like heating your house with a wood stove. If you've been throwing logs on the fire all night, the room gets baking hot. When you finally stop adding wood, the temperature doesn't plunge back to normal immediately. The stove is still glowing, the walls are warm, the air holds heat. It takes hours to cool down. The Early Triassic is Earth's overheated house. Even after the most intense pulses of Siberian volcanism fade, proxy data suggest that global temperatures stay extremely high. Some estimates put equatorial sea surface temperatures well into the 30s Celsius, maybe higher in surface layers during spikes, conditions that push many organisms to the edge of their thermal tolerance. On land, models and sediment evidence point to expanded arid belts, stronger seasonal extremes, and repeated episodes of intense heat stress. The oceans, meanwhile, don't simply flip back from anoxic to well-ventilated. Once large portions of the deep sea lose oxygen, it's hard to reoxygenate them quickly, especially on a hot, stratified planet. Warm water is less dense and holds less dissolved oxygen. Strong thermal layering can cap the surface, limiting mixing with depth. If nutrient cycles are still out of balance, driving algal blooms and decay, you get continuing demand for oxygen at depth. Geochemical records from early Triassic sediments show this lingering sickness. Redox sensitive elements, sulfur isotopes and ion speciation all point to widespread, and in places repeated, Anoxia and even Ozinia, waters enriched in hydrogen sulfide, persisting long after the nominal extinction boundary. It's as if the oceans keep trying to clear their lungs and keep slipping back into respiratory failure. And that's the other key. The aftermath itself isn't smooth. It's punctuated. When researchers zoom in on the early Triassic, they don't see a simple upward curve of biodiversity recovery. They see fits and starts, false dawns where diversity rises a bit, and then crashes again. In some marine groups, like ammonoids and certain bivalves, there are multiple small extinction pulses stacked on top of the main event. These secondary crises seem to line up with continued environmental shocks, renewed warming episodes, fresh intervals of deep-water anoxia spreading onto continental shelves, maybe additional outgassing pulses from the tail end of the Siberian magmatic system. Some sections show repeated negative carbon isotope excursions, geochemical hints that the carbon cycle was still being jolted, perhaps by smaller bursts of greenhouse gases or by abrupt changes in productivity and organic burial. The result is ecological whiplash. Any lineage that starts to diversify into newly open niches suddenly gets hammered by another round of stress. Complex food webs begin to rebuild, then lose key members. Top predators reappear, then disappear. On land, attempts at reforestation may have been repeatedly derailed by heat waves, droughts, fires, and soil instability. Under those conditions, the disaster taxa keep winning. They're the ones that can tolerate fluctuating oxygen, wide temperature ranges, murky water, disturbed soils. They reproduce fast, disperse widely, and don't depend on delicate partnerships like coral-algae symbioses or highly specialized pollination networks that are easily broken in a chaotic climate. This is what delayed recovery looks like on a planetary scale. Not a simple delay in time to evolve new species, but a moving target of habitability. Every time ecosystems try to climb back up the ladder of complexity, the rungs shift. Yet even in this dead zone world, you can see the seeds of resilience. By the middle and late Early Triassic, some groups are experimenting with new strategies. Surviving vertebrates, early archosaurs, for instance, begin to diversify, setting the stage for the later rise of dinosaurs and other Mesozoic reptiles. In the oceans, certain bivalves and gastropods start to occupy more varied ecological roles. Microbial reefs, crude as they are, stabilize sediments and create microhabitats. Patchy vegetation on land slowly improves soil structure, which in turn helps water retention and nutrient cycling. These are the first tentative steps of rebuilding complexity, re-establishing basic ecosystem engineering, recreating gradients of light, oxygen and nutrients that other organisms can exploit. Resilience here doesn't mean bouncing back quickly. It means persistence under terrible conditions long enough for the background stress to ratchet down inch by inch until more elaborate communities can take hold. It would take on the order of 5 to 10 million years for global ecosystems to regain something like pre-extinction levels of diversity and structural complexity. That's dozens of human civilizations stacked end to end, just to move from surviving to living richly again. To see how life finally escaped the dead zone and built the modern-style oceans we recognize today, we have to follow those stubborn survivors into the Middle Triassic, where new winners emerge from the wreckage and start assembling entirely different worlds. Follow those survivors a few million years down the line into the Middle Triassic, and the world is still harsh, but it's no longer stuck on the tutorial screen. The first signs show up in the oceans in places shallow enough to mix with the air and catch some sunlight, but sheltered enough to avoid the worst of the heat and chemical chaos. Here, in scattered basins and continental shelves, complexity begins to creep back in stages. Step 1 is just getting the base of the food web to stabilize. In the early Triassic dead zone, phytoplankton communities were weird and often dominated by opportunistic forms. Repeated anoxia and nutrient shocks kept knocking them back. But as the most extreme oxygen crises become less frequent, and the carbon cycle starts to wobble a little less violently, more normal plankton groups re-enter the scene. Microfossils from Middle Triassic sediments show increasing diversity of algae and planktonic protists. Some of the lineages that will later dominate Mesozoic and modern oceans, like certain radiolarians and dinoflagellates, start to appear or diversify. They're still living on a knife edge, but they're building a more stable, three-dimensional world in the upper water column, different sizes, different depths, different life cycles. That matters, because a richer plankton community means more ways for energy to move through the system. Tiny grazers can specialize. Filter-feeding invertebrates can slot into different tiers. Small fishes and nectonic reptiles can exploit layered resource zones instead of all crowding into the same narrow band of survivable habitat. As the plankton scaffold improves, step 2 kicks in. The seafloor begins to host more than just microbial mush and disaster clams. In many Middle Triassic sections, the monotonous chloria beds thin out. They're joined, and eventually replaced, by more varied bivalves, gastropods, echinoderms, and burrowing worms. You start to see more traces of animals moving through the sediment, complex burrow systems instead of simple surface scrapes. That's ecosystem engineering coming back online. Biotubation, animals churning and mixing the seafloor, isn't just a fun word for paleontologists. It oxygenates the upper layers of sediment, redistributes nutrients, and creates microhabitats. Once burrowers return in force, they help keep local anoxia from locking in at the sediment-water interface. In a very real sense, they ventilate the seabed from below. Then there are the reefs, Permian reefs were dominated by organisms called rugose and tabulate corals and by certain sponges, lineages that get hammered at the boundary and never really recover. The microbialite reefs of the early Triassic are placeholders, structurally important but biologically simple. By the middle Triassic, you start to see new reef systems that look more like the patchwork stage of a burned forest. Pockets of microbial mounds are colonized by sponges, algae, and early scleractinian corals, the group that will later give us the Great Barrier-style reefs of the modern world. These early scleractinians are not a triumphant comeback of old players. They're a different lineage entirely, building a new style of reef architecture. They seem to take advantage of warm, high CO2 waters in ways the old Permian reef builders could not. Some scientists argue that their ability to host symbiotic algae and calcify under variable conditions gave them an edge in this unstable world. Even so, these middle Triassic reefs are patchy, fragile, and often geographically restricted. They wax and wane with local conditions. You don't get a single global reef revolution overnight. You get experiment after experiment, many of which fail. But from this messy trial and error emerges the basic template of modern reef ecosystems, a framework of calcifiers, layered with encrusting organisms, grazers and small predators, all tied into a productive plankton engine offshore. While the seas are rebuilding from the bottom up, evolution is also sorting winners and losers among the survivors. The Great Dying acted as an evolutionary bottleneck. Whole clades of brachiopods, trilobite, like arthropods, and reef dwellers are gone. Others are reduced to a few hardy branches. That loss isn't just sad background. It reshapes what's possible. With many ecological roles vacant and incumbents missing, groups that had been minor in the Permian find themselves with room to run. Bivalves diversify into niches once held by brachiopods. Certain ammonoids explode into a riot of shell shapes and lifestyles, rapidly filling pelagic predator and scavenger roles. Early marine reptiles, ichthyosaurs, nothosaurs and their kin expand into top predator positions that large fishes and Permian amphibians used to hold. This isn't a fair competition. Lineages that made it through the bottleneck are pre-filtered for tolerance to heat, low oxygen and environmental swings. That pre-selection gives them a head start in a Triassic world that never fully goes back to Permian normal. The opportunities are real, but they're contingent on having the right toolkit for a planet still running hot and stressed. On land, a similar reshuffling is underway. The early Triassic landscape of scrappy, weedy plants slowly gives way to more structured vegetation. By the middle Triassic, you start seeing the return of gymnosperm-dominated woodlands and forests, conifers, seed ferns, ginkgophytes, especially in regions where climate has moderated enough to allow deeper soils and more reliable moisture. Once trees come back in force, they restart a whole cascade of terrestrial ecosystem engineering. Deep roots stabilize slopes and riverbanks. Leaf litter builds thicker, more complex soils. Canopies create shade gradients and microclimates. All of this feeds back into weathering rates, the carbon cycle and the hydrological cycle. Animal communities follow. In the Permian, large synapsids, our distant mammal-like relatives, dominated many terrestrial ecosystems. After the extinction, those groups are greatly reduced and never fully reclaim their old status. Instead, archosaurs, the broader group that includes crocodiles, pterosaurs, and eventually dinosaurs, begin to diversify and radiate into herbivore, omnivore, and predator roles. By the late Triassic, this archosaur radiation sets the stage for a new kind of terrestrial world, one where dinosaurs will ultimately become the dominant large land animals for over 100 million years. That outcome wasn't predetermined in the Permian. It emerges from who happened to survive, what traits they carried through the bottleneck, and how the Triassic environment rewarded those traits. Put together, the Middle and Late Triassic look less like a return to normal, and more like the assembly of an entirely different biosphere. Marine food webs are rebuilt around new plankton communities, new reef builders, and new top predators. Terrestrial ecosystems reorganize around conifer forests and archosaur dominance. The old Permian world, a brachiopod-rich, synapsid-dominated planet with different reef architectures and different biogeochemical rhythms, is gone, and the timescale matters. Recovery is not a quick montage, it's 5, 10, even more million years of uneven progress. Diversity rises regionally, then stalls. Some basins recover fast while others lag for reasons that probably include local geography, circulation patterns, and sheer chance. From our perspective, looking back, it's tempting to draw a smooth line from great dying to dinosaurs and coral reefs. But the fossil record pushes back against that neatness. It shows a world feeling its way toward new equilibria, often failing, sometimes succeeding, never guaranteed. Yet by the end of the Triassic, enough of these experiments have stuck that you can recognize the lineaments of the oceans and continents we live with today. Plankton-powered seas with mobile predators, coral-type reefs, burrowed seafloors, tree-stabilized landscapes, and vertebrate-dominated land faunas. The Great Dying didn't just prune the tree of life, it rewired it. The biosphere that emerges on the other side is the one that will carry Earth through the age of dinosaurs, birds, mammals, and eventually us. To see how we know this story in such detail, and how confident we should be, we have to leave the Triassic shorelines behind and go back to the rock itself, to the chemical and fossil traces that let scientists reconstruct a catastrophe and its long, uneasy recovery. If you want to watch scientists argue in slow motion, don't go to a conference. Go to a thin black line in a cliff. That's the Permian-Triassic boundary. In many places, a shift in rock colour, a sharp change in fossil content, maybe a centimetre or two of clay or ash. But inside that narrow interval is where almost everything we've been talking about gets tested. Step 1 is to admit that no single line of evidence is enough. So researchers build what they call a multi-proxy picture. Several independent kinds of clues that all respond to climate, ocean chemistry, or biology in different ways. Start with isotopes, the workhorses of deep time. Carbon isotopes, ratios of carbon-13 to carbon-12, are one of the clearest fingerprints of what the global carbon cycle was doing. When you see a giant, rapid negative swing in delta the 13s across the boundary, that's the rock. Record's way of saying an enormous amount of 12C rich carbon just got dumped into the atmosphere-ocean system. It doesn't tell you who did it, volcanoes, burning coal, methane clathrates, but it tells you something big and fast happened. Oxygen isotopes, usually measured in the shells of tiny marine fossils, act as rough thermometers. Lighter values generally mean warmer water. At the Permian-Triassic boundary, multiple sections show oxygen isotope shifts consistent with rapid warming of surface and even deep waters. Then come the trace metals, elements like molybdenum, uranium, vanadium, and iron change behavior, depending on whether the seafloor is well oxygenated, low oxygen, or outright sulfidic. Build-up of certain metals in those boundary clays and limestone says, the oceans didn't just get warm, they lost breath on a massive scale. In some places, iron speciation data suggest waters went from oxygenated to anoxic to usinic, hydrogen sulfide rich at different depths and times. Layered on top of that, you have the fossils themselves. Fossils tell you who lived and who died, but they also encode patterns of stress. Shrinking body sizes, stunted growth rings in fossil wood, malformed shells in marine invertebrates, spikes in disaster taxa like chloria. These are biological proxies for physiological strain. Palynologists, the people who study fossil pollen and spores, see sudden shifts from diverse forest assemblages to dominance by hardy spore-bearing weed plants at the boundary. That's the land biosphere flinching. Even the sediments, the raw rock without the chemistry, are proxies. Mudrocks turning red or purple hint at oxidizing conditions on land. Sudden changes in grain size and river deposits mark more intense floods, unstable slopes, stripped vegetation. Layers rich in charcoal point to wildfire regimes ramping up under hotter, drier climates. None of these things alone proves global catastrophe. But when carbon isotopes, oxygen isotopes, trace metals, fossils, and sedimentary structures all tilt in the same direction, across multiple continents, the story gets much harder to ignore. To find those patterns, though, you have to sample the planet strategically. Geologists scout what they call boundary sections, places where late Permian rocks pass cleanly into earliest Triassic rocks with minimal gaps. South China, Pakistan, Iran, Italy, Greenland, the western United States, South Africa. Each of these regions preserves its own slice of the event. Cores add a different kind of power. On land, drill cores punch straight through layered basins, capturing continuous records that you'd never see in scattered outcrops. Offshore, scientific ocean drilling pulls up long cylinders of seafloor sediment that record chemistry, tiny fossils, and magnetic flips across the boundary interval. Those cores let scientists trace the same signals, say a sharp delta-13 strop or a spike in anoxia-sensitive metals around the globe. Global correlation is the glue, radiometric dates on volcanic ash beds, magnetic reversal patterns and biostratigraphy, using the first and last appearances of key fossil species are all used to line up these widely scattered records on a single timeline. Only when you can say this spike and that die-off happened at essentially the same time in China and in Italy and in Greenland do you start to see whether the great dying was synchronous or regionally staggered. Even then, the rock record only describes what happened. It doesn't automatically explain why. That's where models come in. Climate and ocean circulation models take known boundary conditions, continent positions, solar luminosity, rough estimates of CO2 levels, volcanic outgassing rates, and ask, if we force the system this way, what happens? When you pump gigatons of CO2 into a Permian world in these models, you do get strong greenhouse warming, weaker temperature gradients between equator and poles, sluggish deep water formation, and large low oxygen zones expanding in the oceans. Ocean biogeochemical models go further, simulating nutrients, plankton, and microbial respiration under those conditions. Some of them naturally produce the kind of widespread anoxia, intermittent ozinia, and carbon isotope behavior we actually see in the rocks, if, and only if, you drive them with CO2 emissions and nutrient pulses at roughly the intensities implied by the Siberian Traps. That alignment between proxy data and model output is what gives scientists more confidence in particular scenarios. If your model of the Siberian Traps can't recreate the scale of warming, the pattern of ocean stagnation, or the timing of oxygen loss that multiple proxies show, you tweak the emissions, the geography, or the feedbacks, or you rethink the hypothesis. Of course, this is where the disagreements bloom. Proxy interpretation is not plug and play. Carbon isotopes can be swayed by local productivity, not just global injections. Trace metals can be remobilized after burial. Bioturbation can smear signals. Different teams might choose different sections, favor different cleaning methods in the lab, or emphasize different correction factors in their calculations. One group's global sudden anoxia can be another group's regional, stepwise deterioration. Even among modelers, choices about cloud feedbacks, mixing schemes, or seafloor respiration can tilt results towards super warm, super stratified ocean versus warm, but patchily ventilated. No one model is the truth. They're tools for testing consistency. Does this physical scenario actually produce a world that looks like the one in the rocks? That's why the field is so hungry for new data. High-precision radiometric dates bracketing the boundary and the main pulses of Siberian volcanism could tighten the timeline from tens of thousands of years to a few thousand, making some causal stories far more likely than others. Better continuous cores from undersampled regions, high latitudes, deep basins, interior continents could reveal whether anoxia and warming really were global and synchronous, or whether there were refuges and time lags. More refined proxies like clumped isotopes for absolute temperatures or novel biomarkers for specific microbial metabolisms could clarify just how hot surface waters got and how far hydrogen sulfide really penetrated into the photic zone. Even reanalyzing classic sections with modern techniques can overturn old assumptions. What used to look like a single extinction horizon can resolve into multiple pulses. Every new constraint either tightens the noose around particular hypotheses or forces people back to the drawing board. And that's the larger point. The story of the Great Dying is not something paleontologists simply found in a rock. It's a constantly updated negotiation between messy local records and global physics-based models, between chemistry and bones, between what we think should have happened and what the Earth actually did. Which raises an uncomfortable but unavoidable question. If we can now read this ancient catastrophe with such resolution, what does it say about the kind of stresses we're currently placing on the same Earth system, and how close we might be to waking up similar feedbacks again? To even ask that question, you have to be careful. The end Permian world is not our world. Different continents, different baseline climate, different life forms, different sun output, different ocean circulation. There was no Antarctic ice sheet to melt, no humans burning fossil fuels, no agriculture, no industrial chemistry. So it's not a script we can just replay with now starring Homo sapiens. It's more like a stress test result. This is what happened the last time the Earth system was shoved hard and fast in a particular direction. The mechanisms matter more than the details, and a few of those mechanisms should make the hair on the back of your neck stand up. Start with carbon. Strip away all the complexity, and the Great Dying has, at its core, a huge, rapid release of carbon into the atmosphere-ocean system. The best estimates for the Siberian Traps and related processes run into the tens of thousands of gigatons of carbon spread over tens to hundreds of thousands of years. That's slower than what we're doing now, but vastly larger in total. When you inject that much CO2, the physics is not mysterious. Greenhouse warming goes up. The atmosphere holds more water vapor, itself a greenhouse gas. Temperature gradients between equator and poles flatten. Winds and ocean currents, which feed on those gradients, weaken and reorganize. Deep water formation slows, oceans stratify, warm, light water on top, cooler, denser, increasingly stagnant water below. The rock record shows all of that indirectly. Warming, oxygen loss, expansion of anoxic, and sometimes sulfidic deep waters. Those are not Permian-only tricks, they are properties of fluid dynamics and radiative transfer. You ramp up greenhouse gases fast enough in a coupled ocean-atmosphere system, and you start to see those same tendencies in models of any era, including the present. Then add chemistry. When CO2 dissolves into seawater, it forms carbonic acid. That acid reacts with carbonate ions, which many marine organisms use to build shells and skeletons. Push the system far enough and the saturation state of key minerals, aragonite, calcite drops. Shell building gets harder, then physiologically expensive, then in some environments almost impossible. In the Permian Triassic boundary sections, you see precisely the pattern you'd expect from a big, fast acidification shock. Carbonate sediments thin or vanish in places, Shell builders crash. Survivors tend to be small, thin-shelled, opportunistic. That's not proof we're heading for the same state, but it is a worked example of what a carbon-driven acidification event can do if it's intense and prolonged enough. Layer on oxygen. Warm water holds less dissolved oxygen. Stratified water is harder to ventilate from the surface. Meanwhile, if warming and nutrient input stimulate productivity, more plankton, more organic matter raining down, microbes in the deep ocean chew through more oxygen as they decompose it. That combination, warmer, more stratified, more biologically active, pushes parts of the ocean past a threshold. You don't get a smooth linear progression from well-oxygenated to slightly low to a bit worse. You get tipping points where vast regions cross into hypoxia or anoxia relatively abruptly. The trace metal and iron data across the Permian Triassic boundary capture exactly those jumps. Again, the underlying logic is not exotic. You see miniature versions today in modern dead zones. River plumes in the Gulf of Mexico, upwelling systems off Namibia, semi-enclosed seas like the Baltic. The Great Dying shows what happens when those mechanisms are not local and seasonal, but global and sustained. This is the first big lesson. Earth system risk is about thresholds and rates of change, not just totals. The total amount of CO2 the Siberian Traps eventually vented matters. But how quickly it was released mattered just as much, maybe more. Rapid forcing gives physical and biological systems less time to adapt, buffer, or redistribute the shock. Weathering reactions that draw CO2 down, the slow growth of carbonate platforms, the evolution or migration of species, all of those operate on their own timescales. If you outrun them, you get pile-ups. You can see that in biodiversity curves around the boundary. Species numbers don't gently slope down as conditions deteriorate. They hang on, wobbling through a stressed late Permian world, and then plunge over a geologically sharp interval. That's what nonlinear collapse looks like. Many stresses accumulating beneath the surface, resilience eroding quietly, until one more increment in temperature or oxygen loss or acidification pushes interconnected ecosystems past their breaking points. It also helps explain why recovery is so painfully slow. Once diversity collapses, the system loses functional redundancy. When a handful of lineages perform most of the key roles, reef building, large herbivory, top predation, losing any one of them hurts disproportionately. The early Triassic dead zone isn't just about hostile climate, it's about ecological networks so thinned out that they can't easily rebuild complexity. Evolution can't instantly regenerate lost clades, and surviving species may be trapped in stressed niches. That's a second warning. Biodiversity loss isn't like draining a battery that you can just recharge at will. It's more like breaking intricate machinery. You can turn off the damaging process. But getting the gears to remesh can take far longer than it took to smash them. At the same time, the Great Dying is not a perfect mirror for today. Our current CO2 pulse is smaller in total, at least so far, but the rate of increase is likely faster than most of what happened at the end of the Permian. The starting climate state is cooler. We still have large ice sheets, modern ocean circulation, and a very different biosphere. We're not triggering the Siberian Traps. We are, in effect, running a different experiment, injecting fossil carbon from coal, oil and gas through industrial combustion rather than through giant volcanic provinces. And there are stabilizing feedbacks and constraints in the modern system that may prevent a full replay of Permian-style eosinic oceans or multi-million-year dead zones, at least at the same scale. Continental positions, mountain ranges, the evolution of grasses and modern plankton, even the presence of humans managing landscapes all change the boundary conditions. But some analogies are hard to ignore. A rapid, geologically instantaneous carbon release. Check. Global warming, especially at high latitudes, narrowing equator to pole temperature gradients, already underway, expanding oxygen pore zones in parts of today's oceans. Measured ongoing acidification documented by direct pH and carbonate saturation observations. Also measured biodiversity under pressure from multiple stressors simultaneously, climate change, habitat loss, pollution, overexploitation. That one doesn't require a proxy. It's visible in real time. The Great Dying doesn't tell us we're doomed to repeat its specific outcome. But it does tell us that when enough of these levers are pushed hard, and especially when they're pushed together, the Earth system is capable of swinging into very different states, states that are hostile to large, complex life and extremely hard to exit. In other words, the rocks at the Permian Triassic boundary are not a prophecy. They're a warning label. This is what happens when carbon, climate, oceans and life all get forced past their comfort zones at once. The question we're left with is not whether our situation is identical. It's how far we're willing to go in testing just how resilient this particular version of the Earth system really is, and whether we can learn from an ancient catastrophe in time to steer away from its most dangerous feedbacks. Before we push into that last stretch, a quick side path for the curiosity addicted among you. If you like following these deep, unresolved threads in Earth's history, I've put together a book on 12 of the strangest, still unexplained mysteries in science and archaeology, things that, like the Great Dying, have a lot of evidence and no single neat answer yet. You can grab it from the site linked in the description. It helps support this channel, and honestly, if you've made it this far into a video about a mass extinction 252 million years ago, you're exactly the kind of person it was written for. Alright, back to the worst day in the last 500 million years. Strip everything we've just covered down to one line, and the story looks like this. Massive, prolonged Siberian volcanism dumped extraordinary amounts of carbon and other gases into the air and oceans, driving rapid warming, acidification, oxygen loss, and toxic feedbacks that cascaded through ecosystems until most complex life collapsed. That's the spine of the narrative. But around that spine, there are still ribs we don't fully understand. For instance, the tempo problem. Was the extinction a single brutal cliff, or a staircase of multiple sharp drops separated by partial recoveries? Different data sets point to slightly different timings. Some sections show a lightning-fast crash in a few tens of thousands of years. Others hint at earlier pulses of stress, smaller die-offs that may have primed the system for the final plunge. How you answer that shapes what you think actually killed most species. Was it one overwhelming blow or accumulated damage that finally crossed a threshold? Then there's the murder weapon question. We know the Siberian Traps loaded the atmosphere with CO2. But was carbon alone enough, or did other killers do a lot of the close-range work? Was it mostly warming plus anoxia? Did sulfide belching microbes turn big swaths of the ocean into a chemical gas chamber? Did methane releases from seafloor hydrates magnify the whole thing into something climate models struggle to reproduce without that extra kick? As we head into the final part of the story, keep those open questions in mind, because they're exactly where the frontier of research is right now. We're at a point where some parts of the Great Dying are on pretty solid ground. We can say with high confidence that there was a gigantic pulse of magmatism in Siberia, right at the right time. We can say that carbon isotopes record one of the largest negative excursions in Earth history, consistent with an enormous injection of isotopically light carbon. We can say oceans warmed dramatically, lost oxygen on a global scale, and in many basins tipped into states where iron and sulfur chemistry scream stratified and stressed. We can say that reefs vanished, forests collapsed, and that it took millions of years for ecosystems to claw their way back to anything like pre-extinction complexity. Those are the anchors. What we're still untangling are the details that turn a broad sketch into a precise mechanism. The exact rates of carbon release, the relative importance of coal combustion versus mantle gases, how much of the killing happened in the deep ocean versus shallow shelves versus on land, whether exotic ideas like impacts or nickel-driven methanogenic blooms played crucial supporting roles or were just background noise, and the fine-grained geography of suffering, why some basins and some clades seem to get hammered early while others hang on until the very end. Think of the rest of this video as sorting fossils into two trays. In one tray, we'll put the parts of the great dying story that are now hard to escape. The carbon pulse, the climate disruption, the ocean chemistry shifts, the long shadow of slow recovery. In the other tray, we'll place the suspects that are still under active investigation: methane clathrates, hydrogen sulfide, coal seam burning, bolide impacts, even subtle quirks in Permian plate tectonics and weathering. We're going to pull those threads together, not to pretend we have a courtroom-style verdict, but to show what best explanation so far looks like when hundreds of geologists, paleontologists, geochemists, and modelers have been arguing about the same catastrophe for decades. So as we turn to that final synthesis, keep two ideas in the back of your mind. First, we know enough to say that the Great Dying was not random bad luck. It was a system being pushed hard, past its limits in ways that leave clear, repeatable signatures in rocks all over the planet. Second, we do not know enough to specify every last step in that collapse. There are still missing pieces, still weird outcrops that don't quite fit, still models that blow up in ways we don't fully trust. The rest of the story is about living with that tension, what it means in practice to learn from an ancient catastrophe when some of its most important details are still just out of reach. So if we step back from the weeds and look at the big picture, what does the Great Dying actually look like today, from the standpoint of hard evidence? It starts with a planet that's already a little fragile. Late Permian Earth has sprawling supercontinents, strange forests and ecosystems that have been running on one basic template for tens of millions of years. Then Siberia blows not one volcano, but a province. A region where magma keeps punching its way up through the crust, again and again, for hundreds of thousands of years, maybe longer. That magma doesn't just ooze politely out of cracks. It forces its way into thick piles of sediments, evaporites, organics, coal seams. It bakes them. It releases CO2, methane, sulfur gases, halogens. The atmosphere, which had been relatively stable, suddenly has a new problem: a massive, sustained flood of greenhouse and toxic gases it can't easily absorb. We see this in the rocks as that enormous negative carbon isotope excursion. Carbon in limestones and organic matter abruptly shifts toward lighter values. Exactly what you expect when huge amounts of isotopically light carbon, volcanic, biogenic, or both, get injected into the system. At roughly the same time, you see temperature proxies, like oxygen isotopes and certain molecular fossils, pointing to rapid global warming. Not a gentle nudge, a spike: warm the air, and you warm the oceans. Warm the oceans and you change how they breathe. Cold water at the poles normally sinks, helping drive circulation and bring oxygen to the deep. But if you heat the surface, reduce temperature gradients, and maybe mess with salinity through changes in rainfall and evaporation, circulation can stagnate. Oxygen doesn't get replenished. The deep ocean starts to suffocate. Redox-sensitive metals, iron speciation, the appearance of black shales loaded with pyrite, and the loss of oxygen-loving fauna all line up with this story: widespread, long-lasting anoxia, and, in many places, ozinia, waters so starved of oxygen that hydrogen sulfide starts to build up. That alone is a nightmare for most marine animals. Add in acidification from all that CO2 dissolving into the water, and you've created a double bind. Carbonate shells dissolve more easily. Larval stages that rely on narrow pH windows get hammered. Reefs, those incredible complex three-dimensional habitats, collapse almost everywhere. On land, the signals echo the same tale. Pollen and plant fossils show forests thinning, then vanishing in many regions. Soil profiles break down. Rivers change from stable, meandering systems with well-developed floodplains to flashy, braided channels stuffed with sediment. That's what you'd expect when roots disappear, hillslops erode, and rain falls on increasingly bare ground. There are charcoal spikes that suggest fires tearing through stressed vegetation. There are vertebrate assemblages that go from diverse to nearly empty, then fill with disaster taxa, small, tough generalists that can survive in hot, open, degraded landscape. This is the core, the part of the story that's now hard to seriously deny. Massive volcanism in Siberia drives carbon release, which drives rapid warming, ocean anoxia, acidification, and habitat collapse on land and at sea. Those Earth system shocks together take out something like 80 to 90% of species. But even inside that relatively solid framework, there are still rooms with the lights off. We don't fully know how fast the carbon came out. Was it a series of brutal pulses when magma hit particularly carbon-rich strata, or a more monotonous but still devastating leak? Did coal seam combustion and contact metamorphism dominate the carbon budget, or were mantle-derived gases enough on their own? Different models can fit the isotope curve with different mixes of sources and rates, and that matters, because the biological impact of the same total carbon dumped over 50,000 years versus 500,000 years is very different. We don't fully know how important the secondary weapons were. Hydrogen sulfide from sulfidic waters rising onto continental shelves is a good candidate for finishing off stressed ecosystems. Methane released from destabilized hydrates on the seafloor could have amplified warming beyond what volcanic CO2 alone would do. Halogen-rich gases might have chewed at the ozone layer, increasing UV stress on land plants and shallow water organisms. The evidence for each of these is suggestive in some sections, weaker in others. They're probably not the main driver, but they could be the difference between a bad extinction and the worst one in Earth history. And we still have to explain the strange geography of survival. Some high-latitude shelf areas seem to hold on to oxygen just long enough for a few lineages to persist. Some burrowing animals, some small opportunistic fish, some hardy plants squeak through. Why them, and not others? Was it physiology, tolerance to heat, low oxygen, low pH? Was it geography, being in the right refugia at the right time? Or was it simply luck, the way random local conditions can sometimes shield a valley when the rest of the region burns? This is where selectivity and recovery become just as important as the kill itself. The Great Dying didn't just wipe the slate, it rewrote the rules about who could play the game. Groups that could handle warm, low-oxygen waters, like some bivalves and modern-style predators, tended to do better in the Triassic oceans than the intricate, filter-feeding reef builders of the Permian. On land, sprawling, shade-tolerant forests gave way, for a long time, to more open, scrubby ecosystems dominated by hardy plants and a narrower set of vertebrates. Recovery was agonizingly slow. For millions of years, you don't see the kind of complex food webs, reef systems and deep forest structures that defined the late Permian. That lag tells us something crucial. Once you push Earth systems past certain thresholds, they don't just snap back when the immediate stress stops. Feedbacks kick in. Warm water holds less oxygen, which kills off organisms that help cycle nutrients. which prolongs anoxia. Lose forests, and you change albedo, erosion rates, the hydrological cycle making it harder for forests to return. The planet can get stuck in a different, simpler state. That's the real warning in this ancient catastrophe. Not that volcanoes are bad or extinctions happen, but that complex systems have tipping points and reinforcing feedbacks. Add stresses together, warming plus anoxia, plus acidification, plus habitat loss, and you don't just get the sum of their individual effects. You can get sudden, irreversible shifts. The Great Dying shows us a world where carbon loading pushed climate and oceans over multiple thresholds at once. It shows us that once those thresholds are crossed, even survivors are living in a fundamentally different world, one that may take millions of years to rebuild anything like the old complexity. It shows us that the early warning signs, rising temperatures, creeping oxygen loss, changing circulation, stressed forests, collapsing reefs, can appear long before the final crash. We're not in a Siberian Traps scenario today. We're humans burning fossil fuels, not basalt provinces intruding into coal states. The magnitudes, timescales, and exact mechanisms are different, but the physics and chemistry of carbon, heat, and oxygen haven't changed. The way feedbacks can take a stressed system and shove it into a new mode hasn't changed either. So if there's a takeaway from the worst day in the last 500 million years, it's this. You don't have to replicate the Great Dying to stumble into some of the same traps. You just have to ignore the early warning signs long enough. If you found this deep dive into Earth's most brutal extinction useful, take a second to like the video, subscribe, and hit the bell so you don't miss future episodes. Drop a comment and tell me where you're listening or watching from. I love seeing how far these stories travel. And if you want to help this kind of long-form, evidence-heavy content keep going, the single best way to support the channel is to listen on Spotify. There's a link in the description. Pop it on during your commute, your workout, whatever works. It helps more than you'd think, and it keeps these ancient warning signs from getting buried again.